Is time travel possible? It's a question that has fascinated scientists, philosophers, and storytellers for centuries. The idea of moving through time, either to the distant future or the deep past, opens up a world of incredible possibilities and perplexing questions. In this video, we'll dive into the scientific theories, paradoxes, and what's truly possible when it comes to traveling through time. Time, as we experience it, seems linear. Seconds turn into minutes, minutes into hours, days into years. But is that the only way to perceive time? According to modern physics, especially Albert Einstein's theory of relativity, time is much more flexible than we might think. Under certain conditions, time can slow down, speed up, or even bend in ways that defy our common understanding. Before we can explore the possibility of time travel, we need to understand what time actually is. Time is often considered the fourth dimension, alongside the three spatial dimensions we're familiar with: length, width, and height. In fact, time and space are interwoven into what scientists call the space-time continuum. This fabric of reality plays a crucial role in how we perceive both space and time. Einstein's theory of relativity changed our understanding of time forever. He showed that time is not constant. It can stretch and shrink depending on speed and gravity. For example, the faster you move through space, the slower you experience time. This phenomenon, known as time dilation, has been confirmed through various experiments, including measuring the decay rates of particles moving at nearly the speed of light. This brings us to one of the most intriguing possibilities for time travel: moving into the future. According to the laws of physics, if you were to travel at an extremely high speed close to the speed of light, time would slow down for you relative to people on Earth. You could, in theory, leap forward in time by experiencing only a few moments while years pass for everyone else. But what about traveling into the past? That's where things get a bit trickier. Theoretical physicists have suggested several possibilities, including wormholes, tunnels through space-time that could, in theory, connect distant points in both space and time. However, these remain purely theoretical, as we've never actually observed a wormhole, much less traveled through one. One of the biggest challenges to time travel, especially to the past, is the problem of paradoxes. Imagine you travel back in time and change something significant, like preventing your own grandparents from meeting. If they never meet, you were never born. But if you were never born, how could you have traveled back in time to stop them? This is known as the grandfather paradox, and it's one of many mind-bending problems associated with time travel. Scientists have proposed various solutions to these paradoxes. Some suggest that time travel might not allow you to alter the past. Instead, everything you do in the past was always part of history. Others propose the existence of parallel universes or alternate timelines, where each change you make creates a new reality, avoiding paradoxes altogether. Even if time travel to the past were possible, it would require an immense amount of energy, far beyond anything we can currently produce. Some theories suggest that you would need something called exotic matter, a form of matter with negative energy density, to hold open a wormhole long enough for a human to travel through. But exotic matter is purely theoretical at this point, making backward time travel a distant dream. Throughout history, the concept of time travel has inspired countless stories, from ancient myths to modern science fiction. Yet, while our understanding of time and the universe has grown dramatically, we are still far from unlocking the secrets of time travel. Time is a concept we interact with every day, but understanding its true nature is far more complex. At its core, time is a measure of change, a way to track the sequence of events from past to future. But what is time made of? Is it simply a tool for humans to organize reality, or is it a fundamental aspect of the universe itself? Scientists describe time as the fourth dimension, existing alongside the three dimensions of space. This notion allows us to think of time as a coordinate, helping us pinpoint where and when things happen. While space lets us move freely in all directions, time flows in only one direction, always moving forward. This one-way flow of time is often referred to as the arrow of time. It gives us the sense that time has a beginning, a middle, and an end. But why does time only move forward? The answer lies in the second law of thermodynamics, which tells us that disorder, or entropy, tends to increase over time, preventing time from running backward. Time isn't just about the ticking of clocks or the changing of seasons. It's a fundamental part of the universe's fabric, intricately tied to space itself. Together, space and time form what's known as spacetime, a concept that revolutionized physics and forever changed how we view reality. Before Einstein's theories, time was thought to be absolute, ticking away at a constant rate no matter where you were or how fast you were moving. But we now know that time is relative. It can stretch and shrink depending on your velocity and the strength of the gravitational field you're in. This is a key component of both general and special relativity. In fact, time is deeply affected by gravity. The stronger the gravitational field, the slower time moves. This phenomenon, known as gravitational time dilation, has been measured in various experiments. For instance, clocks on Earth's surface tick slightly slower than those in orbit, where gravity is weaker. This relativity of time can seem counterintuitive, but it's a well-established part of modern physics. It means that time isn't a fixed universal constant. Rather, it's something that bends and shifts depending on where you are and how you're moving. In extreme environments, such as near a black hole, the effects of time dilation become even more pronounced. Beyond the laws of physics, time also plays a significant role in our perception of reality. It's how we experience change, growth, and decay. Without the passage of time, everything would be frozen, static. But with time, everything flows, allowing the universe to evolve and unfold. Time seems to flow in a continuous stream, but some scientists speculate that time may actually be made up of discrete moments, much like how matter is made of tiny particles. This idea, though still highly speculative, challenges our very understanding of time's nature. In quantum mechanics, the concept of time becomes even stranger. The fundamental laws of quantum theory are time-symmetric, meaning they don't seem to distinguish between past and future. This raises questions about whether the flow of time is as rigid as it seems in our everyday experience. Philosophers and physicists alike have pondered whether time is an illusion. Some argue that time, as we experience it, is a byproduct of our consciousness, a mental construct that helps us make sense of the universe. Others suggest that time is an emergent property of deeper underlying laws of physics. The question of what time truly is remains one of the most profound mysteries in science. Despite our ability to measure it with incredible precision, time continues to evade simple explanation. Is it a real, physical entity? Or is it simply a way for us to understand the changes happening around us? Some interpretations of quantum theory suggest that all moments in time may coexist, like pages in a book, with the past, present, and future already laid out. If this is the case, time as we perceive it could be an illusion, and the future might already exist, waiting to be discovered. In the macroscopic world we live in, time appears to flow in only one direction, moving us from the past toward the future. But at the quantum level, this forward flow may not be so straightforward. Certain quantum phenomena suggest that particles can move backward and forward through time in unpredictable ways. Time, as experienced on the human scale, is intimately tied to our memories and our ability to anticipate the future. This sense of time allows us to plan, to learn from past mistakes, and to imagine possibilities. Without this ability to distinguish past from future, our lives would. Measuring time has been essential to human civilization for thousands of years. From the earlier sundials to today's atomic clocks, the tools we use to track time have become more precise over time. But what exactly are we measuring when we talk about time? At its most basic level, time is measured by observing regular, repeatable processes. In ancient times, people used the movements of the sun, the moon, and the stars to create calendars and mark the passage of days and years. These celestial cycles provided early humans with their first reliable means of measuring time. As civilizations developed, more precise tools were invented. Water clocks and hourglasses offered more consistent measurements of smaller intervals, allowing people to measure hours and minutes with greater accuracy. These early timekeeping devices relied on the steady flow of water or sand to divide time into smaller units. Mechanical clocks, which first appeared in Europe in the Middle Ages, revolutionized how time was measured. With gears, weights, and pendulums, these clocks could keep much more accurate time, regardless of the weather or time of day. By the 17th century, Pendulum clocks became the most precise timekeepers, able to measure seconds for the first time. Then came the invention of the wristwatch and the widespread use of mechanical timekeeping devices in everyday life. Watches and clocks became more accessible and portable, making it easier than ever to track time. The precision of these devices improved as well, but they still relied on physical mechanisms, which were subject to wear and tear. In the 20th century, atomic clocks brought time measurement into a new era of precision. Atomic clocks work by measuring the vibrations of atoms, usually cesium or rubidium, which oscillate at incredibly consistent frequencies. These clocks are so accurate that they can measure time to within billionths of a second. Today, atomic clocks are the gold standard for timekeeping. They are used to set the official time for the entire world, coordinating everything from global positioning systems to telecommunications networks. Even the most sophisticated technologies depend on the precision of atomic clocks to function properly. But even with such precision, we face the challenge of defining exactly what a second is. Since 1967, the International System of Units has defined the second based on the vibrations of a cesium atom, replacing older methods that relied on the Earth's rotation. This definition allows us to measure time independently of natural phenomena, like the movement of planets. Our ability to measure time has become so advanced that we now track its tiny variations. For instance, scientists have discovered that the Earth's rotation is not perfectly uniform, and they sometimes add or subtract leap seconds to keep our clocks in sync with astronomical time. Even the movement of tectonic plates or large storms can cause minuscule shifts in time. The advent of GPS technology relies on incredibly accurate timekeeping to work. Satellites orbiting Earth carry atomic clocks, and their signals are used to calculate distances based on the time it takes for the signals to travel. Without such precise measurements of time, GPS systems would be far less reliable. In space exploration, measuring time becomes even more complex. Time flows differently depending on the gravitational field, as predicted by Einstein's theory of relativity. This means that clocks aboard satellites or space probes experience time differently than clocks on Earth, requiring constant adjustments to ensure accurate timing. Measuring time is not just about tracking the past or predicting the future. It is also about understanding the rhythms of nature and the universe. Biological clocks, like the circadian rhythms that govern sleep cycles, show that living organisms have their own internal measures of time, finely tuned to environmental changes. In recent years, scientists have begun experimenting with new ways to measure time, exploring the possibilities of quantum clocks that could be even more accurate than atomic ones. These cutting-edge developments could push the boundaries of time measurement even further, potentially redefining what we know about the nature of time itself. Despite all the technological advancements, the way we experience time is still deeply connected to the natural world. Seasons, lunar cycles, and the day-night rhythm continue to play an important role in how we perceive time passing. Our ability to measure time may have evolved, but the forces that shape it remain constant. Time measurement has always been about more than just dividing hours and minutes. It's about understanding the order of the universe, coordinating human activities, and connecting us to the past and the future. How we measure time will continue to evolve, just as our understanding of time itself continues to expand. The arrow of time refers to the one-way direction in which time seems to flow. Unlike space, which allows movement in multiple directions, time appears to move only forward, from the past into the future. But why does time have this irreversible flow? The answer lies in the second law of thermodynamics. This law tells us that in any closed system, the total amount of disorder, or entropy, tends to increase over time. As entropy grows, it creates a natural distinction between the past and the future, giving time its forward arrow. In our daily lives, we experience this increasing entropy as the reason things wear out, break down, or become more disorganized. Ice melts, eggs scramble, and buildings decay, all because of entropy. These processes don't spontaneously reverse, which is why we never see a broken vase suddenly reassemble itself. This idea is fundamental to our understanding of time's direction. The increase in entropy provides a clear explanation for why time seems to flow in one direction and not the other. It's a principle we can observe in nearly every aspect of life, from the smallest particles to the largest galaxies. But entropy doesn't just apply to everyday objects, it applies to the entire universe. As the universe expands, its overall entropy increases. Stars burn out, galaxies drift apart, and eventually, all energy will spread out evenly in a state known as heat death. In this distant future, the arrow of time would still exist, but the universe would be in a state of maximum entropy. Interestingly, the universe didn't start out this way. Right after the Big Bang, the universe was in an extremely low entropy state. The relatively ordered state of the early universe is what allowed complex structures like stars, planets, and eventually life to form. The arrow of time was set in motion by this initial condition. The arrow of time is deeply connected to our perception of cause and effect. We think of causes happening before effects, not the other way around. For example, you throw a ball, and then it flies through the air. You don't expect the ball to return to your hand before you throw it. This cause and effect relationship aligns with the forward flow of time. Memory is another key aspect of our experience of time. We remember the past, but we cannot remember the future. Our ability to store and recall memories reinforces our sense of time flowing forward. This difference between past and future is another consequence of the arrow of time. Even in the microscopic world of particles, the arrow of time holds. In the quantum realm, particles interact in ways that also respect the flow of time. While some quantum processes can be time-symmetric, the macroscopic effects of these processes ultimately lead to an increase in entropy. However, there are still unanswered questions about the arrow of time. Some physicists wonder if time might behave differently under extreme conditions, such as inside a black hole. Others speculate about the possibility of reversing time on a quantum level, though this remains purely theoretical. The arrow of time also plays a role in cosmology. As we look further into the past, we see a universe that is less and less disordered. But what came before the Big Bang, and why did the universe begin in such a low entropy state? These questions challenge our understanding of the origins of time itself. While entropy gives us a clear explanation for the arrow of time, it's not the only factor at play. Time dilation, as described by Einstein's theory of relativity, also influences how time is experienced. Near massive objects or at high speeds, time moves more slowly, creating different perspectives on the flow of time. This makes the arrow of time more than just a simple universal concept. Time may flow forward for everyone, but how quickly it flows can vary depending on where you are and how you're moving. This interplay between entropy and relativity gives time a complexity that goes beyond our everyday experience. In the end, the arrow of time remains one of the great mysteries of physics. While we have a solid grasp on why time moves forward, there's still much to learn about its deeper nature. The irreversible march of time shapes our universe, our lives, and everything in between. Yet we're only beginning to uncover its secrets. Einstein's theory of relativity fundamentally changed our understanding of time. According to this theory, time is not a constant, but a variable that changes depending on speed and gravity. This idea breaks from the classical view that time ticks forward at the same rate for everyone. In special relativity, time slows down as you move closer to the speed of light. This phenomenon is called time dilation, and it has been confirmed in various experiments. For example, atomic clocks on fast-moving planes or satellites experience time more slowly compared to clocks on the ground. This means that time isn't an absolute quantity. It depends on your frame of reference, whether you're moving rapidly or standing still. Someone traveling at a significant fraction of the speed of light would age more slowly than someone standing still. General relativity adds another layer to this. Not only does motion affect time, but gravity does as well. The stronger the gravitational field, the more slowly time passes. This is known as gravitational time dilation, and it becomes more noticeable near massive objects like planets or black holes. In practice, this effect is measurable even here on Earth. Clocks at higher altitudes, where gravity is weaker, tick slightly faster than those at sea level. These small differences are taken into account in technologies like GPS, which rely on highly accurate time measurements. Near extremely massive objects like black holes, the effects of time dilation are even more dramatic. If you were to approach a black hole, time for you would slow down relative to someone far away. To an outside observer, it would seem like you were moving in slow motion as you got closer to the event horizon. But for you, time would feel completely normal. This is one of the strange consequences of relativity. Time is relative to the observer's position and speed. What feels like seconds to one person might be years to someone else, depending on the gravitational forces and relative motion involved. Another implication of relativity is the idea of space-time. Time and space are not separate entities, but are intertwined into a single fabric. This means that events are not just located in space, but also in time, and this space-time fabric can be stretched or warped by mass and energy. This warping of space-time explains the effects of gravity in general relativity. Massive objects, like planets or stars, create curves in the space-time fabric, and objects move along these curves. This curvature also affects how time flows, further linking time and space in a fundamental way. Time dilation, whether caused by speed or gravity, leads to the possibility of time travel, at least into the future. If you were to travel at a significant fraction of the speed of light, you could leap forward in time, experiencing only minutes while decades or centuries passed on Earth. However, relativity doesn't provide a clear way to travel backward in time. While forward time travel is theoretically possible, reversing time is much more complicated. The equations of general relativity allow for the possibility of closed timelike curves, but whether these are physically possible remains a matter of debate. Relativity also raises profound philosophical questions. If time is relative and dependent on motion and gravity, then what does that mean for our perception of the present? What one observer considers now may be the past or future for someone else moving at a different speed or in a different gravitational field. Even though time seems constant in our everyday lives, relativity shows us that it's anything but. The passage of time can stretch, contract, and bend, depending on the forces at play. Our understanding of time, grounded in relativity, is much more fluid and dynamic than we ever imagined. In the context of the universe as a whole, relativity helps us understand time on a cosmic scale. From the expanding universe to black holes, the effects of relativity shape everything we know about time and space. Yet there are still unanswered questions about how time behaves under extreme conditions. Einstein's theory of relativity is actually made up of two parts: special relativity and general relativity. Each one deals with different aspects of space, time, and gravity. While both are revolutionary, they address different phenomena and help us understand the universe in distinct ways. Special relativity came first, published by Einstein in 1905. It focuses on how objects behave when they move at constant speeds, especially near the speed of light. One of the key insights of special relativity is that the speed of light is constant for all observers, no matter how fast they are moving. This leads to the idea that time is relative. Time dilation occurs when an object moves close to the speed of light, causing time to slow down for that object relative to an observer at rest. Length contraction, where objects appear shorter in the direction they are moving, is another result of special relativity. Special relativity also introduced the famous equation E=mc2, showing that energy and mass are interchangeable. This equation laid the foundation for understanding how mass can be converted into energy, such as in nuclear reactions, and it demonstrates the deep connection between mass, energy, and the speed of light. But special relativity doesn't take gravity into account. That's where general relativity comes in. In 1915, Einstein expanded his ideas to include the effects of gravity, presenting the world with the theory of general relativity. This theory explains how massive objects warp space and time, creating what we perceive as gravity. In general relativity, gravity is not thought of as a force that pulls objects together. Instead, massive objects like planets and stars cause the fabric of space-time to curve, and other objects follow these curves. This curvature is what we experience as gravity. The stronger the gravitational field, the more space-time is curved, and this affects how time flows. This is why time passes more slowly near massive objects, a concept called gravitational time dilation. The deeper you are in a gravitational well, the slower time moves compared to someone farther away. While special relativity mainly deals with objects moving at constant speeds in a straight line, General relativity applies to objects that are accelerating or are in the presence of strong gravitational fields. It gives us a much more complete picture of how the universe operates on a large scale. One of the most famous predictions of general relativity is the existence of black holes. These are regions of space where the gravitational pull is so strong that not even light can escape. Near a black hole, space-time becomes so warped that time itself slows down dramatically compared to regions far away. Another key difference between the two theories is how they treat reference frames. Special relativity only applies to inertial reference frames, those that are not accelerating. General relativity, on the other hand, can handle reference frames that are accelerating, which makes it more versatile for describing the universe. Special relativity is easier to apply in many situations, especially in the realm of particle physics, where speeds can approach the speed of light. General relativity, however, is necessary for understanding phenomena like planetary motion, the behavior of light in gravitational fields, and the expansion of the universe. The two theories complement each other but are used in different contexts. Special relativity works best in environments without significant gravitational forces, while general relativity is essential when gravity plays a major role. Together, they provide a unified view of space, time, and the universe. Despite their differences, both theories agree on one crucial point: the nature of space and time is not fixed. Instead, space and time are interwoven and dynamic, responding to the presence of mass and energy. This is a radical departure from the Newtonian idea of absolute time and space. General relativity has been tested many times and has passed every challenge so far, from predicting the bending of light by gravity to the detection of gravitational waves. These successes make it one of the most important scientific theories of the modern era, alongside special relativity. Understanding the distinction between these two theories is crucial for grasping how the universe operates on both the smallest and largest scales. Whether you're studying subatomic particles or the vastness of space, relativity gives. Time dilation is one of the most fascinating consequences of Einstein's theory of relativity. It describes how time can move at different rates depending on your speed or proximity to a massive object. This means that time isn't the same for everyone, and it's constantly changing based on your circumstances. When we talk about time dilation, there are two key factors to consider: velocity and gravity. If you're traveling at speeds close to the speed of light, time will slow down for you relative to someone who is stationary. This effect becomes more pronounced the faster you go. This phenomenon has been confirmed by experiments with atomic clocks placed on airplanes or satellites. Clocks moving at high speeds, even those just orbiting the Earth, tick more slowly than clocks on the ground. This demonstrates how, even at relatively low speeds, time dilation can be measured. Gravity also plays a crucial role in time dilation. The stronger the gravitational field, the more time slows down for objects in that field. This is called gravitational time dilation, and it's a key prediction of general relativity. For example, time moves more slowly on Earth's surface than it does in space, far from the planet's gravitational pull. This difference is small, but measurable. It's why GPS satellites, which are farther from the Earth's gravity, need to adjust their clocks to stay synchronized with those on the ground. As you get closer to a massive object, like a planet or star, the effect becomes more dramatic. Near a black hole, where gravity is extremely intense, time slows down significantly compared to someone farther away. In fact, the closer you are to the event horizon, the slower time moves. For someone watching from a distance, it might seem like you're moving in slow motion as you approach a black hole, but for you, time would feel perfectly normal. This difference in how time is experienced is what makes time dilation such a mind-bending concept. One of the most famous thought experiments involving time dilation is the twin paradox. Imagine one twin travels into space at nearly the speed of light, while the other stays on Earth. When the space-traveling twin returns, they would have aged much more slowly than their sibling. This is because time passed differently for each twin due to the effects of velocity. Time dilation doesn't just occur in space or near massive objects, it's happening all around us. It's just that at everyday speeds and gravity levels, the effect is too small to notice. But as technology advances and we explore more extreme environments, time dilation becomes a critical consideration. Even astronauts on the International Space Station experience time dilation. They are moving at high speeds and are slightly farther from Earth's gravitational pull, so their clocks tick more slowly than those on the planet's surface. Over long periods, this small difference adds up. Time dilation shows us that time is not an absolute constant. It can be stretched or compressed depending on the conditions, defying the intuitive idea that time flows at the same rate for everyone. This flexibility of time is one of the key insights of relativity. The closer an object moves to the speed of light, the more time dilation it experiences. At the speed of light itself, time would theoretically stop altogether. This raises interesting possibilities for space travel, where future technologies might allow humans to travel vast distances while only aging a few years in the process. Time dilation is not just a theoretical concept. It has practical implications in fields like astrophysics, space exploration, and even everyday technologies like GPS. Without accounting for time dilation, many of our most advanced systems would simply not work. Understanding time dilation forces us to rethink our basic assumptions about time itself. Instead of a universal clock ticking the same for everyone, we live in a universe where time is fluid, changing depending on where you are and how fast you're moving. As strange as time dilation sounds, it has been tested and confirmed in countless experiments. It is a real effect with real consequences, showing us just how different the universe is from our everyday experiences. The space-time continuum is the framework that combines both space and time into a single unified concept. In classical physics, space and time were seen as separate entities, with time being absolute and space acting as a static backdrop. Einstein's theory of relativity, however, showed that space and time are intertwined. In this continuum, time is treated as the fourth dimension, along with the three spatial dimensions of length, width, and height. This means that events in the universe are not just located in space, but also in time. To describe where and when something happens, you need 4 coordinates, 3 for space and 1 for time. Space-time is flexible and can be stretched or compressed by the presence of mass and energy. Massive objects like planets and stars curve space-time around them. This curvature is what we experience as gravity, guiding the movement of objects through space and even influencing the passage of time. This warping of space-time is the essence of general relativity. Instead of gravity being a force pulling objects together, it's the curvature of space-time that tells objects how to move. The larger the mass, the greater the distortion of space-time, and the stronger the gravitational effects. One of the most striking examples of space-time curvature is found around black holes. The intense mass of a black hole warps space-time to an extreme degree, creating a gravitational well so deep that not even light can escape from it. In this region, the very fabric of the universe behaves in ways that are difficult to fully comprehend. As objects move through space-time, their paths are influenced by this curvature. For instance, planets orbit stars not because they are being pulled by a force, but because they are following the curves of space-time created by the star's mass. This is why planetary orbits appear as ellipses rather than straight lines. The flexibility of the space-time continuum also allows for the possibility of time dilation, where time can pass at different rates in different parts of the universe. A massive object or high velocity can stretch time, slowing it down in one region compared to another. This warping affects both the flow of time and the structure of space. Because space and time are connected, motion through space also affects motion through time. This is one of the core ideas of special relativity. As an object moves faster through space, it moves more slowly through time. The faster you go, the more space-time distorts, and the more extreme the effects become. Visualizing the space-time continuum can be challenging. One common analogy is to think of space-time as a stretchy fabric or rubber sheet. Placing a heavy object on the sheet causes it to sag, just as a massive object curves space-time. Other, smaller objects follow the curves in this sheet, explaining how gravity works. This interconnected nature of space and time leads to many strange possibilities. For instance, if space-time could be warped enough, it might create shortcuts between distant points in the universe. These hypothetical tunnels through space-time are known as wormholes, though they remain purely theoretical for now. Space-time also gives rise to the concept of light cones, which describe the limits of how far light, and therefore information, can travel through the universe. These cones define the boundaries of causality, showing what events can influence one another based on their positions in space and time. The space-time continuum isn't just an abstract idea. It has real, observable consequences. Gravitational lensing, where light from distant stars is bent around massive objects like galaxies, occurs because of the curvature of space-time. This bending of light allows us to see things in space that would otherwise be hidden from view. On the larger scales, space-time is responsible for the overall structure of the universe. Galaxies, stars, and planets all move along paths shaped by the curves of space-time. The expansion of the universe itself can be understood as space-time stretching, pulling galaxies farther apart over billions of years. Our understanding of space-time also extends into quantum mechanics, where the fabric of reality may become even more complex. Some theories suggest that space-time at the smallest scales could be quantized, made up of tiny discrete units, though this remains an area of ongoing research. The space-time continuum remains one of the most profound concepts in modern physics. It forces us to rethink everything we know about the nature of reality, connecting the passage of time to the very shape of the universe itself. Yet we are still exploring its full implications and mysteries. Gravitational time dilation is a phenomenon where time passes at different rates, depending on the strength of the gravitational field. The closer you are to a massive object, the slower time moves for you compared to someone farther away. This effect, predicted by Einstein's theory of general relativity, has been observed and measured in various ways. On Earth, the difference in time is slight, but measurable. For instance, clocks at higher altitudes, where gravity is weaker, tick slightly faster than clocks at sea level. While this difference is tiny, it demonstrates the direct relationship between gravity and the flow of time. In more extreme environments, gravitational time dilation becomes much more pronounced. Near a black hole, where gravity is incredibly strong, time can slow down drastically. Someone near the event horizon of a black hole would experience time moving far more slowly than someone observing from a safe distance. This concept is important for understanding how gravity affects time across the universe. Even light, which moves at a constant speed, experiences the effects of gravitational time dilation. As light escapes from a strong gravitational field, its wavelength stretches, a phenomenon known as gravitational redshift. One of the most famous tests of gravitational time dilation involved atomic clocks flown on airplanes. These clocks showed that time passed more slowly for the clocks in the air compared to those on the ground. This experiment confirmed the predictions of general relativity and demonstrated the reality of gravitational time dilation in everyday situations. This effect is also taken into account in technologies like GPS. The satellites orbiting Earth are farther from the planet's gravitational pull, so their clocks run slightly faster than clocks on the ground. Without correcting for this difference, GPS systems would lose accuracy, drifting by kilometers over time. Gravitational time dilation also plays a crucial role in astrophysics. In the intense gravitational fields of neutron stars, or near the event horizon of black holes, time can be distorted to extreme degrees. For an object falling toward a black hole, time could appear to nearly stop as it approaches the event horizon. To an observer far away, it would seem as though the object took an infinite amount of time to reach the black hole. However, from the perspective of the object itself, time would continue to pass normally. This difference in the experience of time is one of the mind-bending consequences of gravitational time dilation. The slowing of time due to gravity isn't just a theoretical concept. It's been measured on Earth as well. For example, clocks in skyscrapers run slightly faster than those in basements because of the weaker gravitational pull at higher altitudes. While the effect is minuscule, it illustrates how even small changes in gravity can alter the flow of time. This idea that time is affected by gravity has profound implications for our understanding of the universe. It shows that time is not an independent, unchanging entity, but something that can be stretched or compressed depending on the environment. This challenges the classical view of time as an absolute constant. In cosmology, gravitational time dilation affects how we observe distant objects. The light we see from stars or galaxies far from us may have been stretched by the gravitational fields it passed through on its way to Earth. This means that the deeper we look into space, the more we are peering into the effects of gravity on time. Gravitational time dilation is also a key factor in understanding the behavior of black holes. As an object falls toward a black hole, time slows down so dramatically that from an outside perspective, it would never actually appear to cross the event horizon. This creates strange and paradoxical scenarios that scientists are still working to fully comprehend. Even outside of black holes, massive objects like stars can cause time to warp. The more mass an object has, the stronger its gravitational field, and the more pronounced the effect on time becomes. This is why objects near massive stars experience slower time compared to those in less dense areas of space. Ultimately, gravitational time dilation teaches us that time is not a fixed experience. Depending on where you are in the universe, time can move faster or slower, showing just how dynamic the fabric of space-time really is. This fundamental truth continues to reshape our understanding of the cosmos. The speed of light is one of the most fundamental constants in physics. According to Einstein's theory of relativity, nothing can travel faster than light in a vacuum, which moves at about 292 kilometers per second. This limitation is not just a matter of technology, but a rule of the universe itself. As an object approaches the speed of light, its mass effectively increases, requiring more and more energy to keep accelerating. The closer it gets to the speed of light, the more energy is needed, and it becomes impossible to reach or surpass this limit with any finite amount of energy. This rule creates a natural barrier for faster-than-light travel. While science fiction often imagines spaceships breaking this speed, real-world physics suggests this is unlikely. The energy demands become infinite, making it physically impossible for anything with mass to reach the speed of light. For particles without mass, like photons, traveling at the speed of light is natural. But for anything with mass, even the tiniest particle, the laws of physics prevent reaching or exceeding that speed. This limitation defines the structure of space-time and how we experience the universe. Time dilation becomes extreme as you approach light speed. The faster you move, the slower time passes relative to someone who is stationary. If you could travel at near light speeds, time for you might slow to a crawl, but for an observer on Earth, years or even centuries could pass. However, as appealing as this form of time travel might sound, the immense energy requirements and the physical effects on the human body make such travel impractical with our current understanding of physics. Light speed is a hard boundary that governs much of the universe's behavior. Another consequence of the light speed limit is how it defines the causal structure of the universe. Because nothing can travel faster than light, information about events can only travel at that speed. This sets limits on how quickly cause and effect can propagate through space. This limitation is key to why we observe the universe as we do. For example, when we look at distant stars or galaxies, we are seeing them as they were millions or billions of years ago, because the light has taken that long to reach us. The light speed limit creates a kind of cosmic delay in how we experience the universe. In terms of communication, the light speed limit poses a challenge for any potential future space travel. Even with the most advanced technology, sending messages to distant stars would take years, decades, or even longer. This delay is a direct result of the speed of light being the fastest possible transmission speed. Some theoretical ideas, like wormholes or warp drives, have been proposed as ways to bypass the light speed limit. These concepts involve bending or warping space-time itself, creating shortcuts between distant points. However, these remain speculative and unproven within the framework of current physics. Even at a subatomic level, light speed plays a critical role. Particles in particle accelerators are pushed to nearly the speed of light, and their behaviors at these speeds help scientists understand fundamental forces in the universe. But even in these extreme environments, the speed of light remains an insurmountable barrier. One of the strange consequences of the light speed limit is the concept of time becoming essentially frozen at that speed. For something traveling at the speed of light, like a photon, time does not pass at all. From the photon's perspective, it moves instantaneously across any distance, though for us, it takes time to arrive. This barrier also shapes the expansion of the universe itself. While space can expand faster than the speed of light, objects within space cannot. This means there are parts of the universe that are moving away from us faster than light can travel, making them forever unreachable. Despite these limitations, the speed of light defines much of our understanding of physics. It acts as both a universal speed limit and a key to understanding how time, space, and energy interact. Without this fundamental rule, the universe would behave in radically different ways. The light speed limitation isn't just about speed. It's a window into the deep connections between space and time. It shows us the ultimate boundaries of movement and interaction in the universe and forces us to rethink the possibilities of travel, communication, and even the nature of existence. Wormholes are hypothetical tunnels through space-time that could connect distant regions of the universe. They are often referred to as Einstein-Rosen bridges, named after the two physicists who first proposed them. These bridges suggest a shortcut through space and time, offering a possible way to bypass the light speed limit. The concept of a wormhole emerges from the equations of general relativity. According to these equations, if space-time can be curved by mass, it might also be possible for it to fold in on itself, creating a tunnel-like structure. This tunnel could theoretically connect two different points in space-time, allowing for faster-than-light travel. A wormhole consists of two mouths and a throat that connects them. One mouth could be located at one point in the universe, and the other far across space. If you could enter one mouth, you might instantly emerge from the other, even if it's billions of light-years away. Despite the intriguing possibilities, wormholes remain purely theoretical. No experimental evidence has yet confirmed their existence. They are solutions to Einstein's equations, but whether they could actually form in reality is still an open question in physics. One of the biggest challenges with wormholes is their stability. Most theoretical models suggest that a wormhole would collapse almost instantly, closing off the throat before anything could pass through. To keep a wormhole open, it might require exotic matter, a form of matter with negative energy density. Exotic matter is not something we've ever observed directly. Its strange properties would be necessary to counteract the intense gravitational forces that would otherwise collapse the wormhole. Without it, the structure would be too unstable for any form of travel. Even if we could stabilize a wormhole, there are still many questions about how it would function. Would it allow for instantaneous travel between 2 points in space? Or would there still be limitations based on distance and energy? The answers to these questions remain speculative. Another issue is the potential for paradoxes. If a wormhole allows for faster-than-light travel, it could also open the door to time travel. You could, in theory, travel through a wormhole and arrive at a point in the past, creating all sorts of paradoxes, like the grandfather paradox. Wormholes might also connect different universes or distant parts of the same universe. This raises the possibility of parallel universes or alternate realities, though these ideas are even more speculative than the concept of the wormhole itself. They remain in the realm of science fiction for now. In addition to the exotic matter problem, there are significant energy requirements involved. The energy needed to create and maintain a stable wormhole would be astronomical, far beyond anything we can currently produce. This makes the practical creation of a wormhole unlikely with current technology. Wormholes are also predicted to be incredibly small. On the quantum scale, they might exist at sizes too tiny for anything larger than a particle to pass through. Scaling up a wormhole to human size or spaceship size introduces even more complex challenges. Some theories propose that tiny quantum-scale wormholes might exist naturally, but we have no way of detecting them yet. These quantum wormholes could potentially connect different regions of the universe at the smallest scales, but they are far too small to offer any practical means of travel. The study of wormholes continues to be an area of active research in theoretical physics. While no one has found a way to create or detect a wormhole, the concept helps physicists explore the boundaries of what is possible within the laws of physics. Wormholes might also play a role in quantum mechanics. Some physicists have suggested that wormholes could be linked to quantum entanglement, offering a deeper connection between space-time and the quantum world. These ideas are still in the early stages of development. For now, wormholes remain an exciting possibility, but one that is far from becoming a reality. They represent the ultimate frontier in the exploration of space and time, raising questions that challenge our understanding of the universe itself. Closed time-like curves are theoretical paths through space-time that could allow an object to travel back to its own past. They emerge as a possible solution to Einstein's equations of general relativity. If such curves exist, they could make time travel into the past a reality. The idea of a closed time-like curve is based on the concept that time, like space, can loop back on itself. In this loop, an object or person could move forward in time, but eventually return to a point in the past, creating a closed loop. This would allow for travel between different moments in time. One of the simplest ways to imagine a closed time-like curve is to picture space-time as a sheet of paper. If you bend that sheet so that 2 points on the timeline touch, an object could travel from one point to the other, creating a loop in time. Theoretically, this could allow for backward time travel. However, closed time-like curves raise significant concerns about causality. If you can travel back to a previous moment in time, it opens the door to paradoxes. For example, what happens if you change an event in the past that affects your ability to travel back in the first place? One famous example is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you were never born, how could you have traveled back to the past to prevent their meeting? Some physicists suggest that closed time-like curves might avoid paradoxes by making certain events inevitable. In this view, anything you do while traveling through a closed time-like curve was always part of history. No matter what you try to change, the outcome would remain the same. Another possibility is that closed time-like curves might lead to the creation of alternate timelines. When you travel back in time, you could be creating a new branch of reality where events unfold differently, leaving your original timeline unchanged. This would bypass the issue of paradoxes altogether. Despite these theoretical possibilities, closed time-like curves remain highly speculative. There is no experimental evidence to suggest that they exist or that time travel into the past is possible. They remain a mathematical curiosity in the context of general relativity. To create a closed time-like curve, certain conditions would need to be met. These conditions often involve extreme environments, such as those near black holes or within rotating universes. However, such environments are far from anything we can currently access or manipulate. Some researchers have explored the idea of using wormholes to create closed time-like curves. If a stable wormhole could be constructed, it might allow for travel between 2 points in time. But like wormholes themselves, the creation of such a curve would likely require exotic matter and immense amounts of energy. Quantum mechanics also complicates the idea of closed time-like curves. The strange behavior of particles at the quantum level could interfere with, or even prevent the formation of such curves. Integrating quantum theory with general relativity is one of the major challenges in understanding time travel. There's also the question of whether nature itself would allow closed time-like curves to exist. Some physicists believe that the universe might have a chronology protection mechanism, a concept proposed by Stephen Hawking. This mechanism would prevent time travel and the formation of paradoxes by forbidding closed time-like curves from existing. Even if closed time-like curves were possible, the practical challenges of creating and navigating one are immense. The technology required would be far beyond anything we currently have. For now, closed time-like curves remain an intriguing but distant possibility. Closed time-like curves push the boundaries of our understanding of space-time and the nature of reality. They force us to reconsider how time works and whether it is truly linear. Exploring these concepts helps scientists probe the deeper mysteries of the universe. While the existence of closed time-like curves is still a matter of debate, they continue to inspire both theoretical research and science fiction. They represent a frontier of what could be possible, even if we are far from making them a reality. Theoretical time loops are another intriguing possibility in the realm of time travel. A time loop occurs when an individual or object experiences the same sequence of events repeatedly, seemingly stuck in a cycle. While they often appear in science fiction, time loops have a basis in certain interpretations of physics. In a time loop, the future leads back into the past, and the past eventually brings you back to the future. The concept suggests that time could be circular rather than linear, with events repeating themselves endlessly. This raises the question of whether history is fixed or if it could change with each loop. Time loops are closely related to the idea of closed time-like curves. Both involve a scenario where time bends back on itself. In a time loop, however, the events within the loop might play out exactly the same way each time, making it feel like you're reliving the same moment over and over. One of the most famous examples of a time loop is the movie Groundhog Day, where the protagonist lives the same day repeatedly. While this is fiction, the idea touches on the real possibility of a repeating sequence of events in the fabric of space-time. Could the universe itself be caught in such a loop? In theoretical physics, time loops could occur under very specific conditions, such as near-rotating black holes or within a highly curved space-time. These environments could, in theory, bend time in such a way that events repeat in a loop, though no such loops have been observed so far. Quantum mechanics adds another layer of complexity to time loops. Some interpretations of quantum theory suggest that particles might be able to exist in a kind of loop, where their past and future states influence each other. This feedback loop could have strange consequences for how we understand cause and effect. Time loops also challenge our perception of free will. If events repeat exactly the same way each time, does that mean everything is predetermined? Or could small variations in each loop allow for different outcomes? These questions remain largely speculative but offer deep philosophical and scientific debates. Some scientists have proposed that time loops could explain certain anomalies in the universe, such as repeating patterns in the cosmic microwave background. These patterns could suggest that time itself might loop on the largest scales, though this idea is far from proven. The concept of time loops can also be linked to the multiverse theory. If time can loop, perhaps each loop creates a new timeline or alternate universe, where events play out slightly differently each time. This could mean that rather than a single, repeating universe, there are countless variations of each event. Another fascinating aspect of time loops is the potential for learning and growth within them. If someone were aware that they were in a time loop, they could use the repetition to gain knowledge and change their actions in future loops. This idea is often explored in fiction, but raises interesting questions about memory and time. Theoretical time loops also raise concerns about paradoxes. If you can change events within a time loop, could you create contradictions in the timeline? For example, if you prevent an event from happening in one loop, does it erase the loop altogether? These paradoxes make time loops a challenging concept to fully grasp. In the realm of cosmology, some theories suggest that the universe itself could be cyclical, experiencing a series of big bangs and big crunches in an endless loop. This cyclical universe theory would imply that time loops are not just possible, but an inherent feature of the cosmos. While time loops remain a theoretical idea, they help scientists explore the boundaries of what time could be. If time is not strictly linear as we experience it, loops offer a way to think about time in more flexible and dynamic terms. They may also provide insights into deeper laws of the universe. The idea of being trapped in a time loop might seem unsettling, but it also opens the door to new forms of understanding and exploration. Each loop could offer a chance to change the outcome, or to learn something new about the nature of reality itself. Ultimately, theoretical time loops challenge our understanding of time, causality, and the structure of the universe. While they exist primarily in the realm of speculation, they continue to push the boundaries of physics and inspire both scientific inquiry and creative storytelling. And black holes are some of the most extreme objects in the universe, and they have profound effects on both space and time. The immense gravitational pull of a black hole warps the fabric of space-time, creating a distortion that alters how time flows. This phenomenon is known as time dilation. As you get closer to a black hole, the effects of time distortion become more pronounced. To an outside observer, time appears to slow down for anything approaching the black hole. At the event horizon, where the gravitational pull becomes too strong for anything, even light, to escape, time seems to nearly stop. For someone falling into a black hole, however, time would seem to move normally from their perspective. But as they approach the event horizon, they would notice the outside universe speeding up, as if time elsewhere is racing forward. This difference in the perception of time is a direct consequence of general relativity. The event horizon is the point of no return for a black hole. Beyond this boundary, the warping of space-time becomes so extreme that escape is impossible. The closer you get to the event horizon, the more intense the time distortion, with time stretching out infinitely for an outside observer. Inside the event horizon, the laws of physics as we understand them begin to break down. Time and space switch roles in a sense, and everything is pulled inexorably toward the black hole's singularity, a point where gravity becomes infinitely strong, and space-time curvature becomes infinite. Time distortion near black holes isn't just theoretical. Astronomers have observed the slowing of time near massive black holes, such as the one at the center of our galaxy. This slowing down of time affects how light and radiation escape from the region around a black hole, making distant objects appear redshifted. For light escaping from the region near a black hole, the time distortion stretches the wavelengths, making them appear longer and redder. This gravitational redshift is another consequence of how black holes affect time and space. The stronger the gravity, the more extreme the redshift. Time distortion near black holes also opens up the possibility of extreme time travel. If you could somehow survive a journey close to a black hole without falling in, time would pass much more slowly for you compared to the rest of the universe. In theory, you could leap far into the future by spending time near a black hole. However, the intense gravitational forces near a black hole make this kind of travel extremely dangerous. The tidal forces, which stretch and compress objects, would tear apart anything that got too close. This process, often called spaghettification, illustrates just how destructive the environment around a black hole can be. Despite the dangers, black holes remain one of the most fascinating objects for studying time distortion. They represent the ultimate test of Einstein's theory of general relativity, pushing our understanding of gravity and time to its limits. Observing how black holes affect time could provide insights into the fundamental nature of the universe. Time distortion doesn't just happen at the event horizon. Even far outside the black hole, time slows down relative to areas of weaker gravity. This means that massive black holes can influence the flow of time across vast distances, affecting the behavior of stars and planets in their vicinity. For a spacecraft traveling near a black hole, the time dilation would be significant. Time would pass much more slowly for the crew than for people back on Earth. While this might sound like a form of time travel, the reality is that the risks of getting close to a black hole far outweigh the benefits. Another intriguing aspect of black holes is their potential connection to wormholes. Some theories suggest that the extreme warping of spacetime near a black hole could create a tunnel through spacetime, connecting different regions of the universe. While this remains speculative, it raises questions about the role black holes might play in the structure of spacetime. Black holes challenge our understanding of both time and space. They show us that time is not a constant, universal experience, but something that can stretch and bend depending on the environment. As we continue to study black holes, we may uncover new insights into the nature of time itself. The distortion of time near black holes reminds us that our everyday experience of time is just one piece of a much larger puzzle. In the extreme environments of the universe, time behaves in ways that deafen. Exotic matter and negative energy are two concepts that emerge from theoretical physics, particularly in discussions about time travel and wormholes. These forms of matter and energy differ significantly from anything we've observed in the universe so far. They play a crucial role in keeping wormholes stable and preventing them from collapsing. Exotic matter is a type of matter that has unusual properties, including negative mass. In contrast to ordinary matter, which has positive mass and attracts other matter, negative mass would theoretically repel ordinary matter. This repulsive force could counteract the intense gravitational forces inside a wormhole. Negative energy, on the other hand, refers to a situation where energy levels are below what we typically consider the vacuum state, which is the lowest possible energy state in quantum theory. This strange form of energy could be used to keep a wormhole open, balancing the gravitational forces that would otherwise close it. The concept of negative energy comes from quantum mechanics, particularly in phenomena like the Casimir effect. In the Casimir effect, two uncharged plates placed close to each other in a vacuum experience an attractive force due to the quantum fluctuations of energy. These fluctuations suggest the possibility of negative energy existing on very small scales. For a wormhole to remain traversable, exotic matter with negative energy density would need to be present at the mouth of the wormhole. Without it, the gravitational forces would pull the wormhole shut before anything could pass through. However, we have not yet discovered any form of matter or energy with the properties needed for this. The existence of exotic matter or negative energy would challenge many of the assumptions we have about the universe. If they could be harnessed, they might allow for breakthroughs in faster-than-light travel, time travel, or the creation of stable wormholes. But for now, they remain speculative. One of the difficulties in creating or finding exotic matter is that it doesn't fit into our current understanding of the laws of physics. All known matter has positive mass, and all energy we've observed operates within the framework of positive energy states. Exotic matter and negative energy would break these norms. Even though we've never observed exotic matter directly, some theoretical models suggest that it might exist in very specific conditions, such as near black holes or within the quantum realm. However, the energy required to create or detect such matter would be immense, far beyond what we can currently achieve. If exotic matter and negative energy do exist, they could have profound implications for our understanding of space-time. These materials might allow us to manipulate the fabric of the universe in ways that seem impossible now, such as creating artificial gravitational fields or bending space-time for practical purposes. One of the most intriguing possibilities is the role exotic matter could play in constructing a warp drive, similar to what is seen in science fiction. By bending space-time around a spacecraft, a warp drive could theoretically allow faster-than-light travel without violating the laws of relativity. Exotic matter would be a key ingredient in making this a reality. Negative energy might also allow us to explore the concept of time loops or closed timelike curves. If we could generate and control negative energy, it might be possible to bend space-time in such a way that allows for loops in time, potentially opening up pathways for time travel. Even though these ideas sound like science fiction, they are rooted in real scientific theories. However, the practical challenges of discovering or creating exotic matter and negative energy are enormous. Current technologies and scientific understanding are not yet advanced enough to test these ideas fully. The search for exotic matter and negative energy continues in the field of theoretical physics. While no direct evidence has yet been found, their potential to unlock the secrets of time travel and faster-than-light travel keeps scientists interested in their study. The discovery of even a trace of these materials could revolutionize our understanding of the universe. There's also the question of stability. Even if exotic matter or negative energy could be created, maintaining it over large scales and long periods might be difficult. These materials could be highly unstable or require extreme conditions to exist, limiting their practical applications. Ultimately, the discovery of exotic matter and negative energy would force us to rethink many aspects of physics. It would mean that the universe is even stranger than we currently imagine, with possibilities for bending the laws of time and space in ways we are only beginning to comprehend. Quantum superposition is one of the fundamental principles of quantum mechanics. It states that particles can exist in multiple states at once, rather than being in just one defined state. This phenomenon defies the logic of classical physics, where objects are always in one place or condition at a given time. At the quantum level, particles like electrons or photons don't follow the same rules as larger objects. Instead of being in one position or having one energy state, they can exist in a combination of multiple states until they are observed or measured. This strange behavior is a hallmark of quantum mechanics. The famous example of quantum superposition is Schrödinger's cat, a thought experiment that illustrates the concept. In this scenario, a cat in a sealed box can be thought of as both alive and dead until someone opens the box to observe it. The cat represents the superposition of two states, existing in both at once. In quantum superposition, particles like electrons can occupy different positions simultaneously. It's as though the particle is in multiple places at once, only collapsing into one location when it's measured. This creates a reality where the act of observation changes the outcome. Superposition also applies to other properties of particles, such as their spin or energy levels. Until they are measured, these properties exist in a blend of possible states. The uncertainty of a particle's condition is a direct result of its superposition. This concept is closely tied to the idea of wave-particle duality. Particles can behave like waves, spreading out over space and time, and these waves can interfere with each other. Quantum superposition means that a particle can be in a superposition of waveforms each corresponding to a different potential outcome. When a particle is measured, the superposition collapses into a definite state. This collapse happens instantaneously, and the particle assumes one of the possible states. The process of how or why this collapse happens is still one of the mysteries of quantum mechanics. Quantum computers are designed to take advantage of superposition. Unlike classical computers, which use bits that are either 0 or 1, quantum computers use qubits that can exist in a superposition of both states at once. This allows quantum computers to process vast amounts of information simultaneously. Superposition also plays a role in quantum entanglement, where particles become linked and share states, even when they are far apart. If one particle in an entangled pair is measured and its superposition collapses, the other particle's state is instantly determined, regardless of the distance between them. In the world of quantum physics, superposition creates an entirely different view of reality. Instead of objects being in one definite state, the quantum world is filled with uncertainty and potential, where possibilities coexist until they are observed. This challenges our classical understanding of how reality works. Experiments such as the double-slit experiment have demonstrated quantum superposition in action. When particles are not observed, they pass through both slits simultaneously, creating an interference pattern as if they were waves. When observed, however, they behave like particles, passing through just one slit. This dual behavior suggests that at the quantum level, reality is fundamentally probabilistic. Instead of a deterministic universe where outcomes are fixed, quantum mechanics presents a world where multiple outcomes are possible until measurement forces a choice. The implications of superposition extend beyond physics, influencing fields like philosophy and computer science. It raises questions about the nature of reality itself. If particles can exist in multiple states at once, what does that say about the universe we live in? Superposition also leads to the concept of parallel universes in some interpretations of quantum mechanics. Each possible outcome of a quantum event could correspond to a different universe, where every possibility is realized. This is known as the many worlds interpretation. Though we may not fully understand superposition, it remains a cornerstone of quantum theory. It has led to groundbreaking advancements in technology and has opened new avenues for exploring the nature of the universe, even as it continues to challenge our most basic assumptions about reality. Quantum tunneling is another fascinating phenomenon that defies the laws of classical physics. It allows particles to pass through barriers that, according to classical mechanics, they shouldn't be able to cross. This behavior is a direct result of the strange principles governing the quantum world. In classical physics, if an object doesn't have enough energy to overcome a barrier, it's stopped by that barrier. But in quantum mechanics, particles are described as wave functions, and part of that wave can exist on the other side of a barrier, even if the particle doesn't have the energy to cross it directly. Quantum tunneling occurs because there's always a small probability that a particle can tunnel through the barrier and appear on the other side. This isn't because the particle somehow gains more energy, but because its wave function allows for the possibility of being in both places at once. One of the most important applications of quantum tunneling is in nuclear fusion. In stars like our Sun, atomic nuclei fuse together to release energy. These nuclei don't have enough energy to overcome the strong repulsive forces between them through classical means, but tunneling allows them to get close enough to fuse. Quantum tunneling also plays a crucial role in modern technology. In semiconductors, electrons can tunnel through thin barriers in materials, a principle that's essential to the functioning of devices like transistors and diodes. Without tunneling, many of the electronic devices we rely on wouldn't work. In the realm of chemistry, tunneling helps explain certain reactions that occur at lower temperatures than expected. Some chemical bonds can break or form through the tunneling of particles, allowing reactions to proceed even when they don't have enough thermal energy to overcome potential energy barriers. The probability of tunneling decreases as the barrier becomes thicker or higher, but no matter how impenetrable a barrier seems, there is always a tiny chance that quantum tunneling will allow a particle to pass through. This probability makes quantum mechanics a theory based on likelihoods rather than certainties. One of the most striking examples of tunneling is found in the scanning tunneling microscope. This device allows scientists to visualize surfaces at the atomic level, by measuring the tunneling current between a sharp metal tip and the surface. The microscope relies on quantum tunneling to achieve its incredible resolution. In radioactive decay, tunneling is responsible for alpha particles escaping the nucleus of an atom. These particles don't have enough energy to overcome the nuclear forces holding them in, but they can tunnel through the potential energy barrier, allowing the atom to emit radiation. Tunneling challenges the classical view of determinism, where the outcome of an event is fixed if the initial conditions are known. In the quantum world, outcomes are probabilistic, and tunneling reflects this uncertainty. It's a reminder that at the smallest scales, the universe doesn't always follow intuitive rules. Despite its counterintuitive nature, quantum tunneling is a well-verified phenomenon. Experiments have repeatedly confirmed that particles can and do pass through barriers in ways that classical physics can't explain. This has had a profound impact on both fundamental science and practical technology. In addition to its practical applications, tunneling has implications for our understanding of the universe. It shows that particles are not confined to a single location or path. Instead, they exist as probabilities spread out across space, capable of being in places that seem impossible from a classical perspective. Quantum tunneling also offers insight into the probabilistic nature of reality. It challenges the classical idea that particles follow predictable trajectories, revealing a world where uncertainty and chance play a fundamental role. This has led to a deeper exploration of the true nature of reality in quantum mechanics. There are still open questions about tunneling, particularly when it comes to how long it takes for a particle to tunnel through a barrier. This tunneling time is difficult to define, and scientists are still working to fully understand how tunneling operates on the quantum level. Tunneling is a key part of the quantum revolution, providing a bridge between the microscopic world of particles and the macroscopic technologies we use every day. It serves as a reminder of how quantum mechanics reshapes our understanding of what's possible, bending the boundaries of physics as we know it. The many worlds interpretation is one of the most intriguing and controversial ideas in quantum mechanics. It suggests that every time a quantum event occurs, the universe splits into multiple, parallel realities. In each of these realities, every possible outcome of the event happens. According to this interpretation, when a quantum particle exists in a superposition of states, each state corresponds to a different universe. When we observe or measure the particle instead of collapsing into one state, the universe splits and both outcomes occur, but in separate universes. This interpretation was first proposed by physicist Hugh Everett in 1957. It challenges the more traditional view, where the act of measurement forces a quantum system to choose a single outcome. Instead, the many worlds interpretation suggests that all possible outcomes happen, but in different branches of reality. In the many worlds interpretation, every decision, every random quantum fluctuation creates a new universe. In one universe, you might turn left, while in another, you turn right. Both versions of reality coexist, but we only experience one path in our own branch. These parallel universes are not just theoretical constructs. They are as real as the universe we live in, but we have no way of interacting with or observing them. Each universe evolves independently, with its own version of events playing out. The many worlds interpretation eliminates the need for the collapse of the wave function, which is a core concept in other interpretations of quantum mechanics. Instead, the wave function continues to evolve, and each branch of the wave function represents a different universe where a different outcome is realized. This idea raises profound philosophical questions. If every possible outcome happens in some universe, does that mean there are infinite versions of you living out different lives? And what does that say about free will? Are our choices truly our own, or are they just one of many possibilities that all exist somewhere? Some physicists argue that the many worlds interpretation provides a more consistent explanation of quantum mechanics without the need for special rules about observation or measurement. It treats the universe as a single wave function that evolves without collapsing. However, others criticize the interpretation for being untestable. If we can never observe or interact with these other universes, then how can we prove they exist? This has led some to view the many worlds interpretation as more of a philosophical framework than a scientific theory. Despite these criticisms, the many worlds interpretation has gained popularity in recent years, especially among those who seek to explain the strange behaviors of particles in quantum mechanics without relying on the idea of randomness or collapse. It offers a deterministic view of the universe, where everything that can happen does happen. The implications of the many worlds interpretation are vast. If true, it means that there is not just one universe, but a multiverse filled with an unimaginable number of parallel realities. Every event, no matter how small, creates a branching point, leading to a new universe with a different outcome. In the context of time travel, the many worlds interpretation suggests that traveling back in time and changing events wouldn't cause paradoxes. Instead, you would simply create a new branch of the universe where the changes took place, leaving your original timeline untouched. This interpretation also changes how we think about the future. If all possible outcomes already exist in some universe, then the future is not fixed. Instead, it's a web of possibilities, each leading to a different version of reality. While the many worlds interpretation might sound like science fiction, it's a serious proposal that addresses some of the unresolved questions in quantum mechanics. It may never be provable, but it forces us to rethink our understanding of reality, time, and existence itself. The idea of infinite universes challenges the way we perceive our lives and choices. If every possible version of events is real somewhere, it suggests that reality is far more complex and layered than we ever imagined. Quantum entanglement is one of the most mysterious and fascinating phenomena in quantum mechanics. When two particles become entangled, their states are linked in such a way that the state of one particle instantly affects the state of the other, no matter how far apart they are. This connection appears to happen faster than the speed of light. The strange thing about entanglement is that it seems to violate our normal understanding of space and time. If two particles are entangled, measuring one particle immediately determines the state of the other, even if they are separated by vast distances. This instant connection has led to questions about whether information is somehow traveling between the particles faster than light. This phenomenon was so strange that even Einstein famously referred to it as spooky action at a distance. It seems to suggest that entangled particles are somehow connected outside of the normal constraints of space and time. But no one is quite sure how this connection works, or if time plays a role in it at all. One of the key mysteries of quantum entanglement is whether the connection between particles happens instantaneously, or if there is a deeper hidden mechanism we don't yet understand. Some interpretations suggest that the entanglement exists in a timeless state, where space and time don't apply in the way we usually think. Entanglement doesn't just apply to particles close together. Even if the particles are light years apart, the instant one is measured, the other's state is known. This challenges the classical notion that information can only travel at the speed of light and hints at the possibility that time itself may work differently at the quantum level. This connection between entanglement and time has led physicists to question whether time is truly fundamental or if it's an emergent property that arises from deeper quantum laws. In some interpretations, time as we know it may be a byproduct of quantum interactions, not a fundamental feature of the universe. If entanglement isn't bound by the limits of time, it opens up intriguing possibilities for understanding the flow of time itself. Could quantum entanglement hold the key to understanding time travel? If particles can be linked across time as well as space, the implications for our understanding of past and future could be profound. Some experiments have even suggested that entanglement might stretch backward in time. This means that two particles could be entangled in such a way that a future measurement could influence a past state, creating a form of retrocausality. These experiments are highly speculative, but raise important questions about the nature of time. Entanglement also seems to play a crucial role in quantum information and computing. Quantum computers rely on the principle of entanglement to process and store information in ways that classical computers cannot. The manipulation of entangled particles could lead to breakthroughs in how we understand and utilize time in computing. The relationship between entanglement and time also touches on the idea of non-locality. In classical physics, everything that happens is local. It occurs at a specific point in space and time. But entangled particles seem to act non-locally, meaning their connection transcends space and time in ways we don't fully understand. In terms of time, entanglement suggests that the past, present, and future might be more interconnected than we think. If entangled particles can influence each other across space without regard to time, then the traditional linear view of time might be incomplete. This could mean that the quantum world operates under a very different set of rules. This kind of instant connection between particles has also led to speculation about whether entanglement could be used to communicate across time. While this remains a highly theoretical idea, some physicists wonder if understanding how entanglement interacts with time might eventually lead to new ways of thinking about time travel. Despite these possibilities, entanglement remains a deeply puzzling phenomenon. While we've been able to observe and use it in experiments, we still don't fully understand how it works or why it behaves the way it does. The mystery of entanglement continues to challenge our most basic concepts of time and space. Entanglement might also be tied to the structure of space-time itself. Some theories suggest that the very fabric of space-time could be made up of quantum entanglements. If this is true, then time and space are not fundamental properties, but the grandfather paradox is one of the most well-known problems in time travel theory. It presents a logical contradiction that arises when a person travels back in time and changes events in a way that would prevent their own existence. The classic example involves a time traveler preventing their grandfather from meeting their grandmother, thus stopping their parent, and by extension themselves, from being born. This paradox highlights a fundamental problem with altering the past. If the time traveler succeeds in changing history so that they are never born, how could they have traveled back in time in the first place? It's a loop that seems impossible to resolve within the framework of traditional logic. One possible resolution is the idea of self-consistency. In this view, any actions taken by a time traveler were always part of history, meaning that the past cannot be changed. Even if they attempt to alter events, the outcome will ultimately ensure that the future remains unchanged, preserving the time traveler's existence. Another suggestion comes from the many worlds interpretation. According to this theory, traveling back in time would create a new parallel universe. In this new timeline, the traveler's actions could prevent their birth, but their original timeline remains unaffected. This way, the paradox is avoided because the traveler exists in a separate reality. A third possibility involves the concept of closed timelike curves, where events are predestined. In this scenario, time travel is possible, but free will may not be. The time traveler can take actions, but those actions are limited to what has already happened, ensuring that they cannot change the course of history in a way that would prevent their existence. The grandfather paradox forces us to think deeply about the nature of time and causality. In a universe where time travel is possible, does time have a single, unchangeable structure, or is it more flexible? This paradox raises questions about whether the past is set in stone or open to change. If the past can be altered, the paradox suggests that time might be inherently unstable. Every change would lead to a ripple effect, potentially erasing entire timelines or creating endless contradictions. This instability could mean that time travel itself is impossible, as it would lead to too many logical inconsistencies. On the other hand, if the past cannot be changed, it implies a deterministic universe, where every event is fixed and unchangeable. This would mean that free will might be an illusion, and no matter what actions we take, the future is already determined. For some, this idea is just as troubling as the paradox itself. Philosophers and scientists have debated whether the grandfather paradox proves that time travel to the past is impossible. If time travel leads to contradictions, it suggests that the laws of the universe might prohibit such events from occurring, possibly through mechanisms like the chronology protection conjecture proposed by Stephen Hawking. Others argue that the paradox is based on assumptions about time that may not hold true in a quantum or relativistic framework. In quantum mechanics, for instance, events can happen probabilistically rather than deterministically, which might allow for different kinds of time travel without paradoxes. There's also the possibility that time operates in a way we don't fully understand. Some theories suggest that time could be more like a landscape, where different events exist simultaneously, and the experience of moving through time is simply a matter of perspective. This view could resolve the paradox by eliminating the need for cause and effect to follow a strict linear path. The grandfather paradox has also been explored extensively in science fiction. Writers use it to explore the moral and ethical implications of time travel, often portraying characters who must grapple with the consequences of their actions. These stories reflect our deep fascination with the idea of changing the past and the potential dangers that come with it. While the paradox presents a serious challenge to time travel theory, it also sparks creative thinking about how time works. It pushes physicists and philosophers to consider alternatives to our current understanding of time and causality, potentially leading to new insights about the universe. In the end, the grandfather paradox remains unresolved, but it continues to be a valuable thought experiment. It serves as a reminder of the complexities involved in time travel and the need to reconcile our understanding of time with the laws of physics. Whether or not time travel is possible, the paradox shows that our current theories still have gaps to fill. Ultimately, the grandfather paradox leaves us questioning the very nature of reality. If time can be bent, manipulated, or traveled through, what does that mean for the continuity of the universe? And how do we make sense of a world where the past can be rewritten? The bootstrap paradox is another perplexing scenario that arises in time travel discussions. It occurs when an object or piece of information is sent back in time, but its origin becomes a mystery because it creates a self-sustaining loop. Essentially, the object or information exists without ever being created. One common example involves a time traveler who goes back in time and gives Shakespeare a copy of his own works. Shakespeare then publishes these works, which become famous, and the same copy is eventually passed down to the time traveler. The question becomes, who actually wrote the plays? In this paradox, the timeline forms a loop where the origin of the event or object is unclear. Nothing in the timeline seems to account for the creation of the object or information. It simply exists within a self-contained cycle. This creates a paradox where the cause and effect are indistinguishable. Another example could be a person who travels back in time and gives a scientist the plans for a time machine. The scientist builds the time machine, which the original person then uses to go back in time. The paradox is that the time machine exists, but there is no clear point of origin for its invention. The bootstrap paradox challenges the idea that every event must have a clear cause. In a situation like this, the event seems to create itself, defying our usual understanding of causality. This is what makes the paradox so difficult to resolve within traditional concepts of time. Some physicists suggest that the bootstrap paradox could be explained if time is non-linear. In this view, time loops or closed timelike curves could allow events to exist in a self-sustaining way without the need for an external cause. This would mean that certain things in the timeline simply are, without a definite point of origin. The paradox also raises philosophical questions about the nature of existence and knowledge. If information or an object can exist in a loop, where does it come from? Is it possible for something to exist without ever being created? Or is this a breakdown in our understanding of how reality works? In some interpretations, the bootstrap paradox might suggest that the universe itself operates on different rules when it comes to time travel. Rather than breaking causality, these time loops could be a natural part of how time functions on a deeper level, one that we don't yet fully grasp. The paradox also appears in science fiction, where it's often used to explore the strange consequences of time travel. Stories involving objects or knowledge that loop through time without a clear origin highlight the mind-bending possibilities of altering the timeline. These narratives often leave the reader or viewer questioning how reality itself could allow such loops. The name bootstrap paradox comes from the idea of pulling yourself up by your own bootstraps, which is meant to describe an impossible situation. In time travel, the paradox involves events or objects that seem to pull themselves into existence without any external help, much like trying to lift yourself by pulling on your own boots. One possible way to avoid the paradox is through the idea of parallel universes. If time travel creates alternate realities, then the object or information could have been created in one universe and transported to another, where it forms part of a loop. This would mean the paradox only exists within the context of a single universe, but it dissolves when considering a multiverse. Another theory suggests that the paradox might be resolved by a concept called retrocausality, where the future can influence the past. In this case, the object or information might be able to exist because its future state is affecting its past, blurring the lines between cause and effect. Despite these possible explanations, the bootstrap paradox remains an open question in both science and philosophy. It challenges our understanding of time, causality, and the nature of existence, pushing us to rethink how events unfold in a timeline that can loop back on itself. Some believe that if time travel were possible, the universe would somehow prevent paradoxes like this from occurring. This could happen through mechanisms we don't yet understand, perhaps something like Hawking's chronology protection conjecture, which suggests the universe might have built-in safeguards against time travel contradictions. Others argue that paradoxes like these could exist, but would be so rare or isolated that they wouldn't pose a significant problem for the overall structure of time and reality. In this case, self-sustaining loops of information or objects might simply be anomalies in the broader flow of time. While the bootstrap paradox remains unresolved, it continues to fascinate those who think about the possibilities of time travel. It shows how. The predestination paradox is another mind-bending consequence of time travel. In this paradox, a time traveler's actions in the past are what caused the very events that led them to travel back in time in the first place. This creates a closed loop where the traveler is trapped in a cycle of cause and effect. Unlike other paradoxes where time travel seems to introduce contradictions, the predestination paradox doesn't necessarily break the timeline. Instead, it reinforces a series of events that are destined to happen, regardless of any attempt to change them. Everything unfolds exactly as it always has. A classic example involves a person who travels back in time to stop a disaster, only to realize that their actions are what caused the disaster to happen. In this scenario, the traveler's intervention becomes a crucial part of the timeline, ensuring that the event takes place rather than preventing it. This paradox challenges the idea of free will. If the traveler's actions are already part of the timeline, then everything they do was always going to happen. This raises the question of whether they have any real control over their decisions, or if they are simply playing out events that have already been determined. The predestination paradox suggests that time might be fixed and unchangeable. Even if someone has knowledge of future events, any attempt to alter those events could be what sets them in motion. The future, in this case, is not a series of possibilities, but something that is already written. This paradox often appears in stories where characters try to escape their fate, only to find that their attempts lead them directly to it. The very actions they take to avoid their destiny end up being the cause of it. This reinforces the idea that time is a self-contained loop, where cause and effect blur together. In some interpretations, the predestination paradox suggests that time itself has a kind of self-correcting mechanism. No matter what a time traveler does, events will always align in such a way that the timeline remains consistent. The future and the past are inextricably linked, and nothing can break that connection. Philosophically, this paradox raises questions about whether events are predetermined or whether there is room for choice and change. If the timeline is set, then time travel might not offer any real power to alter events. Instead, it merely allows travelers to become part of the chain of causes that lead to the future. Another aspect of the paradox is the question of information or knowledge. If someone travels back in time with knowledge of future events, are they creating those events by sharing that knowledge? In this scenario, the information itself becomes trapped in the same loop, with no clear origin outside of the timeline. Some physicists argue that the predestination paradox could be a natural consequence of time travel within a single, unchanging timeline. If time travel is possible, but the past cannot be changed, then every event would have to fit together perfectly to avoid any contradictions. The paradox, then, is just a reflection of that consistency. However, it's also possible that the paradox reveals a limitation in our understanding of time. If time can be bent or manipulated, it's unclear whether our concepts of cause and effect would still apply in the same way. The paradox forces us to question whether time is linear, or if it's something more complex and interwoven. The paradox often leads to the conclusion that certain events are fated to happen. No matter what actions are taken, the timeline will unfold as it always has, locking the time traveler into a role they cannot avoid. This deterministic view of time suggests that the future is not something we can change, only experience. In science fiction, the predestination paradox is often used to create stories where characters are both the cause and effect of their own journeys. These narratives explore the tension between destiny and free will, often leaving the characters with a sense of inevitability as they realize they can't escape their role in the timeline. The paradox also illustrates the difficulty in separating cause from effect when time travel is involved. If future events can influence the past, and vice versa, then our understanding of linear time may be flawed. The predestination paradox suggests that time might be more of a loop than a straight line. Ultimately, the predestination paradox is a reminder that time travel might not give us the power to change the past or the future. Instead, it could simply reveal how interconnected all events are, locking us into a destiny that cannot be rewritten. Traveling near the speed of light is a fascinating concept rooted in the principles of relativity. As an object approaches this incredible speed, the effects of time dilation become significant. Time slows down for the traveler compared to those remaining stationary, meaning that they would age more slowly during their journey. The effects of time dilation can be illustrated with the famous thought experiment involving twin paradoxes. Imagine one twin travels on a spaceship at near light speed while the other stays on Earth. When the traveling twin returns, they will be younger than their Earthbound sibling due to the time dilation experienced during the journey. Achieving speeds close to light requires immense amounts of energy. As an object accelerates towards this speed, its mass effectively increases, which in turn requires even more energy to continue accelerating. This means that reaching light speed is practically impossible for any object with mass. In practical terms, current technology can only get us a fraction of the way to light speed. Even the fastest spacecraft we have launched fall far short of the necessary speeds. However, ongoing research into propulsion technologies such as ion drives or theoretical concepts like warp drives aims to increase our capabilities. One of the key principles of special relativity is that nothing can exceed the speed of light. This limit is a fundamental aspect of how space and time are interconnected. Crossing this threshold would lead to scenarios that contradict our current understanding of physics, such as traveling back in time. If humans were able to travel at speeds approaching light, the implications for exploration would be profound. A journey to distant stars could take a matter of years for the travelers, while decades or centuries might pass on Earth. This creates intriguing possibilities for long-term space missions. The relativistic effects become even more pronounced as speeds increase. At a significant fraction of light speed, not only does time slow down for the traveler, but distances also contract in the direction of travel. This means that traveling vast distances could feel much shorter to those on board the spacecraft. The phenomenon of relativistic mass increase is a challenge for any spacecraft designed for such speeds. As the spacecraft accelerates, it would require more fuel to maintain its velocity. Engineers and physicists must find solutions to this challenge if we are to make light-speed travel feasible. Additionally, the vast distances of space pose challenges in terms of navigation and communication. Traveling close to light speed would mean that signals sent back to Earth would take longer to reach their destination. This could complicate mission planning and coordination, especially over interstellar distances. Cosmic rays and other forms of radiation pose another danger for travelers moving at these incredible speeds. The energy of particles in space increases dramatically as speed increases, potentially leading to hazardous conditions. Spacecraft would need advanced shielding to protect against these dangers. In the realm of science fiction, light-speed travel often involves concepts like warp drives or wormholes. These ideas allow for faster-than-light travel by bending or warping space-time itself. While purely theoretical, they capture the imagination and inspire ongoing research into new methods of space travel. Traveling at near light speed also leads to intriguing philosophical questions. How would such journeys affect our perception of time and reality? Would encountering time dilation change our understanding of life and relationships back on Earth? Despite the challenges, the quest for near-light speed travel inspires innovation and exploration. Advances in technology and our understanding of physics may one day allow humanity to reach the stars. The potential for discovering new worlds drives scientists and engineers to pursue ambitious projects. While we are far from achieving light-speed travel, the concepts behind it continue to push the boundaries of science. The principles of relativity not only inform our understanding of the universe, but also inspire new generations of thinkers and dreamers. As we learn more, the possibilities for the future of space travel remain exciting and open-ended. Cryonics is the practice of preserving individuals at extremely low temperatures after death, with the hope that future medical advancements will allow for revival. The underlying idea is that by halting biological processes, including decay, a person can be kept in a state that might enable future resuscitation. While the technology is still experimental, it raises intriguing questions about life, death, and the potential for time travel. Suspended animation, a related concept, involves slowing down bodily functions to the point where metabolism nearly ceases. This technique is often explored in the context of long-duration space travel, where it might allow astronauts to endure long journeys without aging significantly. Both cryonics and suspended animation aim to extend the possibility of life beyond current biological limits. In cryonics, the preservation process begins immediately after legal death is declared. The body is cooled to slow metabolic processes and prevent ice formation within cells. Special cryoprotectants are then introduced to minimize damage during freezing, as ice crystals can destroy cellular structures. Despite its potential, cryonics is fraught with scientific and ethical challenges. One major concern is whether the preservation methods used can actually maintain the integrity of the brain and other tissues. If critical information is lost during the preservation process, the chances of successful revival diminish significantly. Additionally, the legality of cryonics raises questions. Currently, cryonics is considered a form of advanced medical treatment, but it occurs under conditions that differ from traditional medical practices. The lack of regulatory standards contributes to skepticism about its effectiveness and safety. The future of cryonics also depends on advancements in biotechnology and medicine. If scientists discover methods to repair cellular damage caused by the freezing process, the potential for successful revival increases. However, this technology is still theoretical, leaving many uncertainties surrounding the practice. Suspended animation has been depicted in science fiction as a way to explore distant galaxies without the effects of aging. This method would allow astronauts to enter a state of deep sleep for the duration of their journey, awakening only upon arrival at their destination. The feasibility of this concept hinges on the ability to safely induce and reverse suspended animation. In some research, scientists have experimented with techniques to induce suspended animation in small mammals. These studies involve cooling the body, lowering heart rates, and using various compounds to slow metabolism. While promising, translating these techniques to humans presents significant challenges. One major concern regarding suspended animation is the potential impact on human consciousness and memory. If a person were to undergo this process, would they experience a seamless transition when revived? The implications for identity and continuity raise complex philosophical questions. Ethical considerations also come into play with both cryonics and suspended animation. Questions about consent, the potential for exploitation, and the societal implications of extending life must be carefully considered. The idea of reviving individuals in a future society poses challenges related to social integration and identity. As technology progresses, the lines between life, death, and preservation may blur. Cryonics and suspended animation present fascinating possibilities for human longevity, but they also require careful scrutiny. The intersection of ethics, science, and philosophy will be crucial in navigating these advancements. Public perception of cryonics and suspended animation varies widely. Some view them as cutting-edge approaches to extending life, while others see them as unscientific or even unethical. This divide shapes the ongoing debate about the legitimacy and potential of these practices. Ultimately, the exploration of cryonics and suspended animation invites us to consider our understanding of mortality and the future of humanity. As we advance scientifically, the possibilities for extending life could challenge traditional notions of death and what it means to be human. These ideas continue to captivate the imagination and inspire research in diverse fields. Time dilation in high-speed travel is a fascinating consequence of Einstein's theory of relativity. As an object approaches the speed of light, time for that object slows down compared to a stationary observer. This effect becomes significant at velocities close to the speed of light, fundamentally altering our understanding of time. One of the most striking examples of time dilation occurs in particle physics. Subatomic particles like muons, created in cosmic rays, travel towards Earth at nearly the speed of light. Because they are moving so fast, their decay time appears longer when measured from Earth, allowing them to travel farther than they would if they were at rest. In practical terms, astronauts aboard a spacecraft traveling at high speeds would experience time differently than people on Earth. For those on the spacecraft, time would pass normally, but upon their return they would find that more time has elapsed on Earth. This means they could potentially return to a future where decades or even centuries have passed. This phenomenon has been experimentally verified through atomic clocks placed on fast-moving aircraft or satellites. These clocks, when compared to stationary clocks on the ground, show measurable differences in time elapsed due to their high velocities. Such experiments provide real-world evidence for the predictions made by relativity. The implications of time dilation extend beyond mere curiosity. They pose challenges for future space travel. If humanity is to explore distant planets or stars, the effects of time dilation must be taken into account. Long journeys could mean that travelers age more slowly than those remaining on Earth, leading to complex social and personal dynamics. Traveling at high speeds also leads to length contraction, another aspect of relativity. As an object approaches light speed, its length in the direction of travel appears to contract from the perspective of an outside observer. This phenomenon further illustrates how our conventional understanding of space and time can be fundamentally altered at relativistic speeds. To visualize these effects, consider a spacecraft traveling at 90% of the speed of light. For the crew aboard the ship, everything feels normal. But for someone observing from Earth, the journey seems to take much longer. This discrepancy highlights the relativity of time and how different observers can perceive the same event in vastly different ways. As we look toward the future, harnessing high-speed travel may one day be feasible. Advanced propulsion technologies, such as ion drives or hypothetical warp drives, could allow spacecraft to reach velocities approaching the speed of light. Understanding time dilation will be critical in planning missions that span years or decades. Even at lower speeds, time dilation can still have noticeable effects, albeit to a lesser degree. Aircraft flying at high altitudes experience a slight increase in clock speed due to the weaker gravitational field compared to sea level. While the differences are minuscule, they remind us that time is influenced by both speed and gravity. In considering the ethical implications of high-speed travel, the disparity in aging between travelers and those on Earth raises complex questions. How would society adapt if space travelers returned significantly younger than their peers? These social dynamics could challenge our perceptions of relationships, time, and identity. Furthermore, long-term missions involving time dilation could impact the planning and execution of future explorations. Crew members would need to be prepared for the reality that their experiences may differ drastically from those left behind. Psychological effects of returning to a world that has moved on could be profound and require careful consideration. Time dilation also invites deeper philosophical reflections on the nature of time itself. If time can stretch and contract, what does that mean for our understanding of reality? The experience of time could become highly subjective, leading to a re-evaluation of how we measure our lives. In light of these considerations, scientists and researchers continue to study the implications of time dilation. Future technologies could lead to advancements in both our understanding of physics and our ability to travel beyond our planet. As we push the boundaries of exploration, time dilation will remain a key factor in shaping our journey through the cosmos. With ongoing research into the effects of high-speed travel, we may discover new ways to mitigate the challenges posed by time dilation. Advances in technology and our understanding of physics could pave the way for interstellar journeys. As we look to the stars, the mysteries of time and space will undoubtedly influence our path forward. Space travel introduces fascinating complexities related to the nature of time. As astronauts venture beyond Earth, the effects of relativity become increasingly significant. Both time dilation and the vast distances involved in space exploration challenge our conventional understanding of time. When traveling at high speeds, as previously discussed, time for astronauts slows down compared to people on Earth. This means that on long-duration missions, crew members could return to find that more time has passed on the planet than they experienced in space. Such discrepancies have profound implications for both personal relationships and scientific research. The distances in space also affect our perception of time. When observing celestial objects, we often see them as they were millions or even billions of years ago, due to the time it takes for light to travel to us. This means that our view of the universe is inherently a glimpse into the past, complicating our understanding of current events in the cosmos. For missions to distant planets or stars, the time required for travel can stretch over years or decades. This brings about challenges in mission planning, crew selection, and the psychological well-being of astronauts. Prolonged isolation in space can have significant effects on mental health, emphasizing the importance of support systems. As we look toward missions to Mars or beyond, the effects of time will play a crucial role in designing spacecraft and life support systems. Ensuring that astronauts can cope with the challenges of long-term space travel requires careful consideration of the physical and psychological aspects of time spent away from Earth. Moreover, the difference in time experienced by astronauts compared to people on Earth can lead to complications in mission objectives. For example, research on aging and biological processes in space must account for the time discrepancies when analyzing results. Understanding how time impacts human physiology during space travel is essential for future missions. The technology used in space travel must also adapt to the challenges posed by time. For instance, communication with mission control could be affected by the time it takes for signals to travel across vast distances. This latency means that astronauts must often rely on their training and judgment, as immediate support may not be available. In addition, as spacecraft journey farther from Earth, they may encounter varying gravitational fields that influence time. According to general relativity, time runs differently in stronger gravitational fields, which means that every part of a journey could yield different experiences of time. This variability must be taken into account for accurate mission planning. The concept of time also ties into the exploration of black holes and their effects on space-time. Approaching a black hole would significantly alter how time is experienced, with extreme time dilation occurring near the event horizon. This poses both risks and opportunities for future exploratory missions. While human space travel is currently limited to our solar system, advances in technology could one day enable journeys to other star systems. These voyages could take years, if not decades, and time dilation would become an even more critical factor in planning. Understanding how time behaves in different contexts will be essential for successful long-distance exploration. Space travel also provides a unique opportunity to study time itself. By conducting experiments in microgravity, scientists can gain insights into the effects of time on biological processes, materials, and fundamental physics. The microgravity environment serves as a natural laboratory for understanding the relationship between time and space. As we consider the future of space exploration, the interplay between time and travel will only become more relevant. The advancements we make in understanding time in space can potentially revolutionize our approach to exploration. Time itself, as a dimension, will shape the trajectories of our journeys into the cosmos. In the realm of science fiction, the relationship between time and space travel often serves as a backdrop for intriguing narratives. Stories explore the philosophical implications of time dilation, parallel universes, and the nature of reality. These imaginative scenarios inspire ongoing discussions about our future in the stars. Ultimately, the complexities of time in space travel challenge our perceptions and prompt deeper inquiries into the fabric of the universe. The study of time, in relation to space travel, opens new avenues for exploration and understanding. As we push further into the cosmos, the mysteries of time will continue to guide our journey. Human limitations present significant challenges when it comes to time travel and exploration of the cosmos. Our biological needs, such as oxygen, food, and water, impose constraints on how long we can venture into space. These necessities require careful planning for long-duration missions, especially to distant destinations. The effects of microgravity on the human body are also a major concern. Prolonged exposure can lead to muscular atrophy, bone density loss, and other health issues. As we send astronauts on longer missions, understanding and mitigating these effects becomes increasingly critical for their well-being. Psychological factors further complicate long-term space travel. Isolation and confinement can lead to stress, anxiety, and interpersonal conflicts among crew members. Maintaining mental health during extended missions requires robust support systems and strategies to help astronauts cope with the challenges of space. Another limitation arises from our current technological capabilities. While we've made significant advancements in space travel, our propulsion systems are still relatively slow. Reaching distant stars remains a formidable challenge, as existing technology may not be sufficient for such journeys. Radiation exposure poses a serious risk for astronauts traveling beyond Earth's protective atmosphere. Cosmic rays and solar radiation can increase the likelihood of cancer and other health issues. Developing effective shielding and monitoring systems will be essential for safeguarding human health during deep space missions. Our understanding of time itself is still evolving, which adds complexity to time travel concepts. While theories like relativity provide frameworks, the practical implications of these theories on human experience remain largely unexplored. This gap in understanding presents a challenge for envisioning the future of human time travel. Additionally, the aging process is a natural limitation that we cannot escape. As we explore the possibility of long-duration missions, the effects of aging on astronauts become significant. Solutions such as suspended animation or advanced medical interventions may be necessary to address this issue. Physical fitness is crucial for anyone embarking on a space journey. Astronauts must undergo extensive training to prepare their bodies for the rigors of space travel. Ensuring that crew members remain in peak physical condition throughout their missions is vital for their health and performance. Communication delays also present a practical limitation in space travel. As spacecraft travel farther from Earth, the time it takes for signals to reach mission control increases. This latency can hinder decision-making processes, requiring astronauts to rely on their training and judgment. Cultural and societal factors influence our approach to space exploration as well. Public interest and funding for space missions can fluctuate, impacting the resources available for research and development. Balancing public support with the needs of scientific advancement is an ongoing challenge. Our current understanding of the universe is still limited. While we have made significant discoveries, many questions remain unanswered about the nature of space, time, and human existence. Expanding our knowledge base is essential for addressing the complexities of time travel and exploration. Ethical considerations also come into play as we contemplate time travel and its implications. Questions about consent, the potential for exploitation, and the impact on society need careful examination. Navigating these ethical dilemmas will be crucial as we advance our understanding of time and space. Human limitations extend beyond physical and psychological aspects. They also encompass our perceptions and beliefs about time. Many of our assumptions about reality are shaped by our experiences, which may not apply in the context of time travel. Challenging these perceptions is necessary for expanding our understanding. As we look toward the future, interdisciplinary collaboration will be key to overcoming human limitations in space travel. Physicists, engineers, psychologists, and medical professionals must work together to create comprehensive solutions. This holistic approach will help us address the multifaceted challenges of exploring the cosmos. In summary, the limitations of humanity are both practical and philosophical. While we have made strides in technology and understanding, significant obstacles remain. Overcoming these limitations will require innovation, cooperation, and a willingness to rethink our assumptions about time and existence. The question of whether time travel is possible has intrigued scientists, philosophers, and dreamers for generations. Theoretical frameworks in physics, particularly Einstein's theories of relativity, suggest that certain forms of time travel might be feasible. However, practical implementations of these theories remain a distant aspiration. In the realm of special relativity, time dilation offers a glimpse into how time can behave differently under certain conditions. As an object approaches the speed of light, time for that object slows relative to an outside observer. This suggests that traveling forward in time is not only possible but already occurs for objects moving at high velocities. General relativity opens the door to more exotic possibilities, including the concept of wormholes. These hypothetical structures could connect distant points in space-time, potentially allowing for shortcuts through the universe. However, the existence of stable wormholes has yet to be confirmed, and creating one would likely require exotic matter or energy. The idea of closed timelike curves also enters the conversation when discussing backward time travel. These curves could theoretically allow a person to return to a previous point in time. However, the implications of such travel raise profound questions about causality and the nature of reality itself. Quantum mechanics introduces additional complexities to the discussion of time travel. Concepts like quantum superposition and entanglement hint at possibilities that defy our traditional understanding of cause and effect. While these phenomena are well established in the quantum realm, applying them to macroscopic time travel remains speculative. One major obstacle in the pursuit of time travel is the energy required to manipulate space-time effectively. Current technology is far from achieving the necessary energy levels for creating stable wormholes or accelerating objects to near-light speeds. Without significant breakthroughs in energy production and understanding, practical time travel may remain out of reach. Philosophical considerations also play a significant role in the discussion of time travel. If time travel were possible, it could fundamentally alter our understanding of free will, destiny, and causality. The implications of being able to change the past or explore the future challenge our concepts of morality and ethics. Various theoretical solutions have been proposed to address the paradoxes associated with time travel. Concepts such as the Novikov self-consistency principle suggest that any actions taken in the past would be self-consistent, preventing contradictions. In this framework, time travel could be feasible without causing logical inconsistencies. Despite the challenges, ongoing research in physics continues to explore the frontiers of time travel. Scientists are investigating the properties of black holes, wormholes, and quantum phenomena to better understand the nature of time. Each discovery brings us a step closer to answering the question of whether time travel could someday be a reality. Public interest in time travel fuels speculative discussions and imaginative storytelling in literature and film. These narratives often explore the consequences of altering time, presenting both the wonders and dangers of such power. While fictional, these stories inspire curiosity and fuel scientific inquiry. The potential for time travel raises practical considerations for future exploration and technology. If we could harness the principles of time dilation or manipulate space-time, our approach to interstellar travel might change dramatically. Humanity's quest for knowledge could expand beyond our current limitations. As we continue to explore the universe, the intersection of time travel and technology will be crucial. Future advancements in propulsion, energy, and materials science may open doors previously thought impossible. The journey toward understanding time travel reflects our innate desire to push boundaries and explore the unknown. While time travel remains a theoretical endeavor, the exploration of its possibilities encourages innovative thinking. Each step forward in our understanding of physics may lead to new opportunities for exploration and discovery. The quest for time travel embodies humanity's unyielding curiosity about the universe and our place within it. In summary, while the possibility of time travel remains uncertain, the scientific exploration of its principles continues to provoke thought and inspire. Theoretical frameworks suggest intriguing avenues worth investigating, yet practical challenges abound. As research progresses, the dream of time travel may inch closer to reality, inviting us to ponder its implications for humanity. Wormholes, often depicted in science fiction, are hypothetical passages through space-time that could create shortcuts between distant points in the universe. Theoretical physics suggests that these structures might allow for faster-than-light travel by connecting two separate locations in space-time. Their unique properties make them a captivating topic for both scientists and enthusiasts alike. In essence, a wormhole consists of two mouths connected by a throat. If these structures could be stabilized, they would theoretically allow objects or information to travel from one mouth to the other almost instantaneously. This could revolutionize our understanding of travel and exploration beyond our solar system. The concept of wormholes arises from the equations of general relativity. Einstein's theories describe how mass and energy warp the fabric of space-time, and under certain conditions, this warping could lead to the formation of a wormhole. However, the existence of such structures remains purely theoretical at this stage. One of the significant challenges is the stability of a wormhole. Most theoretical models suggest that they would collapse almost instantly after forming unless held open by exotic matter. This exotic matter would need negative energy density to counteract the immense gravitational forces at play. While wormholes present exciting possibilities, they also introduce complex questions about causality. If a wormhole allows travel between 2 points in time, it could potentially enable paradoxes similar to those seen in time travel discussions. The implications of such travel raise important philosophical and scientific questions. Experiments to detect wormholes directly have yet to be conducted, primarily because their existence remains hypothetical. Some scientists believe that observing certain cosmic phenomena, such as gravitational waves or unusual patterns in the cosmic microwave background, might provide indirect evidence for wormholes. Until then, their status remains uncertain. In theoretical frameworks, traversable wormholes could connect distant regions of space, making interstellar travel feasible within human lifetimes. This would open up the universe for exploration, allowing humanity to reach stars and galaxies that are currently unreachable with existing technology. The potential for expanding our horizons is immense. The notion of using wormholes for practical travel brings challenges regarding energy requirements. The amount of energy needed to create and maintain a stable wormhole is currently beyond our capabilities. Future advancements in technology may be necessary to unlock the potential of these structures. There are also concerns about safety when it comes to traversing a wormhole. The unknown nature of such a journey raises questions about the effects on human physiology and technology. Understanding the risks involved is essential before attempting any practical applications. In addition to their scientific implications, wormholes have captured the imagination of writers and filmmakers. Many stories explore the concept of traveling through wormholes, often leading to alternate realities or time travel. These narratives reflect our fascination with the unknown and the possibilities of exploring beyond our current limits. The study of wormholes could also shed light on the fundamental nature of the universe. Investigating these structures may lead to new insights into the fabric of space-time, gravity, and the fundamental forces that govern our reality. The quest for understanding wormholes may unlock secrets that have eluded scientists for centuries. While wormholes are still theoretical, their exploration may guide future research in both physics and cosmology. As scientists work to better understand the universe, the study of wormholes offers a pathway to explore some of its most profound mysteries. Each step forward could illuminate our understanding of how the cosmos operates. In the context of advanced propulsion systems, wormholes could play a vital role in humanity's future in space. If we can harness the principles behind these structures, the logistics of long-distance travel may change drastically. This could enable a new era of exploration, transforming our relationship with the universe. As research progresses, the intersection of quantum physics and relativity may provide further insights into the feasibility of wormholes. Understanding how these concepts intertwine could lead to breakthroughs in our understanding of time, space, and the very fabric of reality. The journey into the unknown promises to challenge our existing paradigms. In summary, the exploration of wormholes as pathways through space-time represents an exciting frontier in theoretical physics. The potential for travel across vast distances captures our imagination and drives scientific inquiry. While many questions remain, the quest to understand wormholes continues to inspire both research and wonder. Cosmic strings are hypothetical one-dimensional defects in the fabric of space-time, predicted by certain theories in cosmology. These theoretical structures may have formed during the early universe, possibly as a result of phase transitions in the fabric of space-time itself. Their existence could provide insights into the fundamental nature of the universe. According to the cosmic strings theory, these strings are incredibly dense and can stretch across vast distances. Despite their thinness, they could possess mass, leading to gravitational effects on the surrounding space-time. This unique characteristic makes them fascinating objects for study in the context of both cosmology and theoretical physics. One interesting feature of cosmic strings is their ability to warp space-time. The gravitational field around a cosmic string could create unique effects, such as bending light or altering the paths of nearby objects. This warping could, in theory, produce observable phenomena that scientists might detect. Cosmic strings are also theorized to be connected to the early moments of the universe, particularly during the inflationary period. This rapid expansion could have caused defects in the newly formed spacetime, resulting in cosmic strings. Studying these strings may help us understand the conditions that existed in the universe shortly after the Big Bang. If cosmic strings exist, they could potentially be linked to the formation of galaxies. Their gravitational influence might have played a role in how matter clustered in the early universe, contributing to the large-scale structure we observe today. This connection makes cosmic strings a critical area of research for understanding cosmic evolution. Another intriguing aspect of cosmic strings is their potential relationship with wormholes. Some theories suggest that cosmic strings could serve as the foundation for creating traversable wormholes. By exploiting the unique properties of these strings, it might be possible to connect distant points in space-time. The detection of cosmic strings presents significant challenges. They would likely be very thin and difficult to observe directly, but their gravitational effects could leave imprints on the cosmic microwave background radiation. Analyzing these effects could provide evidence for their existence and shed light on their properties. Additionally, cosmic strings might interact with other cosmic phenomena, such as dark matter or black holes. Understanding these interactions could help refine our models of the universe. The implications of cosmic strings extend beyond mere theoretical speculation and could have real consequences for our understanding of fundamental physics. The study of cosmic strings also raises important questions about the nature of space-time itself. If these structures exist, they would challenge our current models and push the boundaries of our understanding. They could provide a deeper insight into the mechanics of the universe at both cosmological and quantum levels. In theoretical frameworks, cosmic strings might serve as clues to understanding unifying theories that combine gravity with quantum mechanics. This intersection could offer a pathway to new discoveries in physics, potentially leading to a theory of everything. The quest to understand cosmic strings may illuminate the links between gravity, quantum theory, and the fabric of the cosmos. Cosmic strings have been the subject of many scientific studies and simulations, aiming to model their behavior and potential effects on the universe. These simulations help researchers predict how cosmic strings would interact with light and matter. Observational data gathered from experiments could confirm or refute the existence of these intriguing structures. While the concept of cosmic strings might seem abstract, it embodies the search for understanding in a universe that often defies intuition. Theoretical research into these structures helps refine our models and prepares us for future explorations. Each discovery brings us closer to unlocking the mysteries of the universe. In the broader context of cosmology, cosmic strings fit into discussions about the early universe and the nature of cosmic inflation. Their study allows us to explore the processes that shape the universe as we know it. Understanding cosmic strings could lead to insights that fundamentally alter our view of cosmic history. The exploration of cosmic strings continues to captivate physicists and cosmologists alike. As technology advances and our observational capabilities improve, we may one day uncover the existence of these fascinating structures. Their potential to reshape our understanding of the universe makes them a compelling focus for ongoing research. Energy requirements for time travel and space exploration present significant challenges that researchers must address. The concept of traveling at or near the speed of light necessitates vast amounts of energy, far beyond what current technology can produce. Understanding these energy demands is crucial for any future endeavors into time travel or long-distance space journeys. In the context of special relativity, as an object's speed approaches light, its relativistic mass increases. This means that more energy is required to continue accelerating the object. The energy needed to propel a spacecraft at high velocities raises questions about the feasibility of such missions. For theoretical constructs like wormholes, the energy requirements become even more daunting. Creating and stabilizing a traversable wormhole would likely require exotic matter with negative energy density. Currently, the existence of such matter remains purely hypothetical, complicating the prospects for practical applications. The concept of energy extraction from natural sources also enters the discussion. Some proposals suggest harnessing the energy of stars or black holes to fuel advanced propulsion systems. If successful, these methods could provide the immense energy needed for interstellar travel. Another approach involves exploring advanced propulsion technologies, such as ion drives or fusion engines. These systems could offer more efficient means of propulsion, potentially reducing the energy required for long-distance space missions. Innovations in these technologies are crucial for expanding our capabilities in space exploration. In addition to propulsion, energy requirements extend to life support systems for long-duration missions. Maintaining a stable environment for astronauts involves generating oxygen, recycling water, and providing food. The energy needed for these systems must be carefully considered when planning extended missions. The energy consumption associated with communication also plays a role in space travel. As spacecraft travel farther from Earth, the power needed to maintain contact increases. This aspect of energy requirements must be factored into mission planning to ensure reliable communication. Long-term space missions may necessitate the development of self-sustaining systems to minimize energy demands. These systems would rely on renewable resources, such as solar power, to maintain their operations. Efficient energy management will be crucial for the success of future exploratory missions. The study of energy requirements can also lead to advancements in materials science. Developing lighter and more efficient materials for spacecraft can help reduce overall energy consumption. Innovations in materials technology will enhance our ability to build craft capable of enduring the challenges of deep space travel. Understanding the interplay between energy requirements and the laws of physics is essential for advancing our knowledge of time travel. If we can identify ways to minimize energy demands while adhering to the principles of relativity, the dream of time travel may become more attainable. Researchers are constantly exploring these possibilities to unlock new avenues for exploration. Furthermore, international collaboration may play a key role in addressing energy challenges. Joint efforts among countries can lead to shared resources and expertise, helping to tackle the significant energy demands of space travel. Collaborative projects could pave the way for breakthroughs in technology and understanding. While the energy requirements for time travel remain largely theoretical, they prompt ongoing research in various scientific fields. As we strive to unlock the mysteries of the universe, understanding energy demands will be fundamental. Each discovery in this area can contribute to our overall goals of exploration and understanding. The intersection of energy requirements and human limitations highlights the complexities of future space missions. Overcoming these challenges will require innovative thinking and technological advancements. Addressing energy demands is crucial for making time travel and deep space exploration a reality. As we explore the energy landscape for potential solutions, the quest for new sources of power remains vital. Harnessing renewable energy or developing novel propulsion methods could significantly change the trajectory of human space travel. The journey towards sustainable exploration requires a multifaceted approach to energy production and consumption. The universe presents a variety of constraints that shape our understanding of time travel and exploration. One major limitation is the vast distances between celestial bodies, making interstellar travel a monumental challenge. The sheer scale of the universe demands innovative solutions to overcome these spatial barriers. Gravity plays a significant role in the constraints we face. Massive objects like planets and stars warp space-time, creating gravitational fields that can affect the trajectories of spacecraft. Navigating these gravitational influences is crucial for planning effective travel routes through space. The laws of thermodynamics impose additional constraints on space travel. Energy conservation dictates that we cannot create energy from nothing, which limits the feasibility of certain propulsion systems. Understanding these laws is essential for developing technologies that can efficiently harness energy for space missions. Cosmic radiation is another major concern for long-duration space travel. As astronauts venture beyond Earth's protective atmosphere, they are exposed to higher levels of radiation. This exposure can pose significant health risks, necessitating effective shielding and monitoring to protect crew members. The finite lifespan of spacecraft is a critical consideration as well. Materials and systems degrade over time, particularly when subjected to harsh space environments. This limitation requires careful design and engineering to ensure that spacecraft can withstand extended missions. Time itself poses unique constraints in the context of relativistic travel. As speeds approach the speed of light, time dilation alters the experience of time for travelers. This discrepancy complicates mission planning and can affect the relationships between astronauts and those remaining on Earth. Furthermore, our current understanding of physics places limits on the methods available for time travel. Theoretical frameworks provide insight into concepts like wormholes, but the practical implementation of such ideas remains untested. These constraints highlight the gap between theoretical possibilities and actual capabilities. Resource limitations also play a critical role in space exploration. Developing and maintaining the infrastructure necessary for long missions requires significant investments in technology and funding. The availability of resources affects our ability to conduct exploratory missions beyond our immediate environment. Human limitations introduce additional constraints that must be considered. The physical and psychological effects of long-duration space travel can impact crew performance and health. Addressing these human factors is essential for the success of future missions. The interplay of political and social factors can also constrain our exploration efforts. Funding for space missions often depends on public interest and governmental priorities, which can fluctuate over time. Navigating these political landscapes is crucial for ensuring the continuity of ambitious projects. In addition, the ethical implications of exploration must be considered. As we venture into new frontiers, we must grapple with the consequences of our actions, both for ourselves and for potential extraterrestrial environments. These ethical considerations shape the narrative of our journey into the cosmos. Environmental constraints on Earth also impact our ability to explore space. Issues such as climate change and resource depletion demand attention and action. As we pursue space exploration, we must also consider the sustainability of our planet and the responsible use of its resources. Communication delays present a practical limitation for deep space missions. As spacecraft travel further from Earth, the time it takes for signals to reach mission control increases. This latency complicates real-time decision-making and requires astronauts to rely heavily on their training. The mysteries of dark matter and dark energy add further complexity to our understanding of the universe. These phenomena remain poorly understood, yet they appear to influence the behavior of the cosmos. As we seek to unlock the secrets of the universe, these constraints will guide our research and exploration. Ultimately, the constraints imposed by the universe challenge our creativity and innovation. They require us to rethink our approaches to space travel and exploration. Understanding these limitations can inspire new technologies and strategies as we embark on our journey into the unknown. The violation of causality is one of the most intriguing challenges presented by the concept of time travel. Causality, the principle that cause precedes effect, is a fundamental aspect of our understanding of the universe. When time travel enters the equation, this linear progression can become convoluted and problematic. One of the most famous examples of this violation is the grandfather paradox. If a time traveler goes back and prevents their grandfather from meeting their grandmother, it raises questions about their own existence. This contradiction highlights the complexities that arise when attempting to change events in the past. The potential for causality violations invites a host of philosophical inquiries. If time travelers can alter past events, what does that mean for our understanding of free will? This intersection of choice and consequence becomes a fertile ground for debate among scholars and thinkers. In theoretical discussions, some physicists propose that causality may be preserved in ways we do not yet fully understand. Concepts like the Novikov self-consistency principle suggest that any actions taken by a time traveler must ultimately align with the existing timeline. This framework prevents contradictions by ensuring that any changes are inherently self-consistent. Another possibility is the existence of multiple timelines or parallel universes. In this view, changes made by a time traveler would create a new branch of reality, leaving the original timeline intact. This would allow for the coexistence of different versions of events without violating causality. The idea of retrocausality introduces further complexity to the discussion. If future events can influence the past, the traditional flow of cause and effect becomes less clear. This notion challenges our fundamental understanding of time and raises questions about the nature of reality itself. In narratives that explore time travel, violations of causality often serve as pivotal plot points. Characters may face moral dilemmas arising from their attempts to change the past, leading to unintended consequences. These stories highlight the fragility of causality and the potential chaos of meddling with time. Scientific explorations of causality violations can also be found in quantum mechanics. Certain interpretations suggest that particles can exist in superposition, leading to outcomes that challenge classical notions of causality. This raises questions about the relationship between quantum phenomena and our macroscopic understanding of time. If causality can be violated, it forces us to reconsider the nature of time itself. Is time a rigid structure, or is it more fluid, allowing for variations based on circumstance? Engaging with these ideas can deepen our understanding of the complexities inherent in the fabric of the universe. The implications of violating causality extend to our ethical considerations as well. If individuals can change past events without regard for consequences, what responsibilities do they bear? This ethical dimension becomes crucial in discussions about the potential for time travel. As scientists and philosophers continue to investigate the concept of causality, new theories may emerge. Understanding how time travel might interact with the principles of causality could reshape our perspective on the universe. Each discovery contributes to a more nuanced comprehension of time and its implications. The possibility of causality violations also raises questions about determinism and free will. If the timeline is fixed, does that mean our choices are predetermined? Alternatively, if changes can be made, how does that influence our understanding of agency and choice? In speculative fiction, violations of causality often lead to unexpected twists and thought-provoking scenarios. These narratives encourage audiences to ponder the implications of altering the past and the nature of reality. Such stories serve as cautionary tales about the dangers of manipulating time. The exploration of causality and its potential violations is a rich field for scientific inquiry. As we push the boundaries of our understanding, we may uncover new principles that govern time and space. This journey into the unknown invites us to question our assumptions and deepen our knowledge of the universe. Ultimately, the topic of causality violation prompts us to reflect on the fundamental nature of time and existence. Engaging with these concepts allows us to confront the complexities of reality. As we explore the implications of time travel, we must grapple with the intricacies of cause and effect. Energy and resource requirements for time travel and deep space exploration are critical considerations in theoretical discussions. Achieving the velocities necessary for time travel would demand an extraordinary amount of energy, far beyond our current technological capabilities. Understanding these energy needs is essential for any future advancements in time travel. The concept of harnessing energy efficiently becomes paramount when considering propulsion systems. Traditional fuel sources may not provide enough power for the ambitious goals of interstellar travel or temporal navigation. Researchers are exploring alternative methods, such as nuclear fusion or antimatter propulsion, which could offer the necessary energy density. If wormholes were to be used for travel, the energy requirements for stabilizing such structures would be immense. Theoretical models suggest that exotic matter with negative energy density would be necessary to keep a wormhole open. Currently, the existence and creation of this exotic matter remain purely speculative. In the realm of long-duration space missions, life support systems must also be considered. Providing a stable environment for astronauts involves generating oxygen, recycling water, and growing food. Each of these systems requires energy, and finding efficient ways to sustain them during lengthy missions is vital. Solar power is one potential source of energy for space missions, especially for those close to the sun. Solar panels can capture sunlight and convert it into usable energy, but their effectiveness diminishes with distance. As missions venture farther from the sun, alternative energy sources must be explored. Energy storage becomes another challenge in the context of space travel. Efficiently storing energy for use during critical phases of a mission is essential. Advances in battery technology or the development of new materials could enhance our ability to store and utilize energy effectively in space. Additionally, the infrastructure needed for space travel involves significant resource investment. Building spacecraft, life support systems, and research facilities requires extensive materials and funding. Coordinating these resources presents logistical challenges that must be addressed as exploration ambitions grow. Research into resource utilization in space has gained traction as well. Technologies that can extract resources from asteroids or other celestial bodies could reduce reliance on Earth-based supplies. This prospect opens new avenues for sustainable space exploration, enabling missions to draw on local resources. As we consider the implications of time travel, The energy and resource requirements underscore the importance of interdisciplinary collaboration. Engineers, physicists, and environmental scientists must work together to develop viable solutions. This collaborative effort can lead to breakthroughs in our understanding of energy and resource management. The potential for harnessing energy from natural phenomena is also worth exploring. For instance, capturing the energy from cosmic rays or harnessing gravitational forces may offer innovative solutions for powering spacecraft. Investigating these possibilities could change the landscape of space exploration. Moreover, ethical considerations regarding resource allocation arise in the context of space exploration. As we strive to unlock the mysteries of the universe, we must also be mindful of the environmental impact on Earth. Balancing the pursuit of knowledge with responsible stewardship of our planet is essential. In the future, advancements in energy technology may provide new pathways for time travel and exploration. Understanding the principles of energy manipulation could lead to revolutionary changes in our capabilities. Each discovery in this field can contribute to the overarching goal of expanding human presence in the cosmos. Energy efficiency will play a crucial role in shaping the future of space travel. Developing technologies that minimize energy consumption while maximizing output is essential for sustainable exploration. As we progress, the importance of energy management will only become more pronounced. Ultimately, the study of energy and resource requirements serves as a foundation for our aspirations in time travel and exploration. Engaging with these complexities enables us to imagine a future where the boundaries of our universe are within reach. As we advance our understanding, the pursuit of energy solutions will remain at the forefront of our endeavors. The unstable nature of wormholes presents significant challenges in the realm of theoretical physics. Although they offer intriguing possibilities for shortcuts through space-time, current models suggest that they may be inherently unstable. This instability could prevent any practical use of wormholes for time travel or interstellar journeys. One of the primary concerns regarding wormhole stability is the immense gravitational forces at play. When matter passes through a wormhole, it can create intense stresses that lead to collapse. This means that maintaining a traversable wormhole long enough for safe passage would require sophisticated solutions. To keep a wormhole open, some theories propose the need for exotic matter with negative energy density. This exotic matter could counteract the gravitational forces trying to close the wormhole. However, the existence of such matter remains purely theoretical and has not been observed in nature. The dynamics of a wormhole are also affected by its size and shape. A larger wormhole might be more stable than a smaller one, but the exact parameters needed for stability are still unknown. Understanding the interplay of these factors is crucial for any potential future applications of wormholes. In addition, the environment surrounding a wormhole could impact its stability. For instance, passing near massive celestial bodies might exert additional gravitational influence, destabilizing the wormhole. Navigating these complexities adds another layer of difficulty to the concept of using wormholes for travel. Theoretical research continues to explore the conditions necessary for a stable wormhole. Simulations and mathematical models aim to identify parameters that could allow for the creation and maintenance of these structures. As our understanding deepens, we may uncover new insights into the fundamental nature of space-time. The potential risks associated with traversing a wormhole are also significant. If a wormhole were to collapse while an object or individual is inside, the consequences could be catastrophic. This risk underscores the need for caution in any theoretical exploration of wormhole travel. Furthermore, the behavior of matter and energy as they interact with a wormhole remains poorly understood. How would particles behave as they entered and exited such a structure? These questions highlight the gaps in our knowledge about the fundamental physics involved in wormhole dynamics. In the context of time travel, the unstable nature of wormholes poses additional complications. If a time traveler were to use a wormhole to access the past, the risks of collapse could prevent them from returning safely. This uncertainty raises questions about the feasibility of using wormholes for temporal navigation. The search for stable wormholes may also lead to advancements in other areas of physics. As researchers investigate the properties of these structures, they might uncover new principles governing space-time. This exploration could enhance our understanding of gravity and the fundamental forces of nature. The possibility of harnessing wormholes for practical use invites ethical considerations as well. If such technology were developed, how would it be regulated? The implications of using wormholes for travel, exploration, or even military purposes must be carefully examined. Despite the challenges, the allure of wormholes continues to inspire scientific inquiry and speculation. Theoretical physicists are driven by the potential to unlock new frontiers in our understanding of the universe. Each step forward in this research opens new avenues for exploration. As we probe the mysteries of wormholes, we are reminded of the vastness and complexity of the cosmos. The quest to understand these structures is intertwined with our fundamental desire to explore and expand our horizons. The unstable nature of wormholes only serves to highlight the intricacies of space-time. The exploration of wormholes reflects the human spirit of curiosity and innovation. While practical applications may remain out of reach for now, the pursuit of knowledge continues to inspire future generations. Engaging with the complexities of wormholes may eventually lead us to new insights about the universe. Hawking's chronology protection conjecture is a fascinating idea proposed by physicist Stephen Hawking. This conjecture suggests that the laws of physics prevent time travel into the past, effectively protecting the timeline from paradoxes. According to Hawking, any attempt to create a time machine would lead to mechanisms that would stop it from functioning. The conjecture stems from the understanding that while general relativity allows for the possibility of time travel through concepts like wormholes, these constructs would likely be inherently unstable. Hawking theorized that natural processes in the universe would act to eliminate any potential for time travel that could disrupt causality. This implies that the universe has built-in safeguards against violations of time. One of the key aspects of the conjecture is its focus on the stability of space-time. If time travel were possible, it could lead to paradoxes like the grandfather paradox, creating logical contradictions. By positing that time travel is fundamentally impossible, Hawking's conjecture aims to maintain the integrity of the timeline. Hawking's ideas have sparked extensive debate among physicists and philosophers. While some support his conjecture, others argue that the potential for time travel should not be dismissed outright. The discussions surrounding his ideas contribute to the broader exploration of time, causality, and the fabric of the universe. In theoretical scenarios, Hawking suggested that if time machines could exist, they would have to adhere to certain constraints that prevent paradoxical outcomes. This could mean that any attempt to change the past would inadvertently lead to outcomes that preserve the original timeline. This notion aligns with the self-consistency principle discussed in other theories. The conjecture also raises important questions about the nature of time itself. If time travel to the past is impossible, what does that mean for our understanding of free will and determinism? The interplay between these concepts is essential to grasping the implications of Hawking's work. Moreover, Hawking's chronology protection conjecture encourages researchers to delve deeper into the nature of black holes and their effects on space-time. The behavior of matter and energy near black holes might provide insights into the mechanisms that safeguard causality. Understanding these dynamics could lead to new discoveries in both theoretical and observational physics. The conjecture has implications for the search for advanced propulsion systems and time travel technologies. If the universe indeed prohibits backward time travel, scientists may need to focus their efforts on alternative methods of exploration. This redirection of research could foster innovations in other areas of physics. Hawking's ideas also emphasize the importance of observational evidence in shaping our understanding of time travel. While theoretical models are valuable, they must be tested against empirical data to validate their claims. This scientific rigor is crucial in evaluating the feasibility of concepts related to time and causality. The philosophical dimensions of Hawking's conjecture invite further exploration into the ethics of time travel. If time travel were to become possible, the ethical implications of altering past events would need to be addressed. Engaging with these questions helps us consider the responsibility that would accompany such powerful capabilities. Additionally, the conjecture highlights the limits of our current understanding of physics. As researchers continue to study the fundamental laws of the universe, new insights may emerge that challenge existing theories. This ongoing exploration keeps the dialogue alive regarding the nature of time and its potential for manipulation. In popular culture, Hawking's ideas have inspired numerous works of fiction that explore the concept of time travel. These narratives often grapple with the consequences of altering history and the inherent risks involved. Such stories serve to reflect our fascination with the possibilities and dangers of manipulating time. Hawking's work continues to influence contemporary discussions on the subject. His contributions have shaped our understanding of black holes, time, and the nature of reality itself. The legacy of his conjecture remains relevant as we investigate the complexities of the universe. The chronology protection conjecture may not provide definitive answers, but it serves as a guiding principle for future research. Its emphasis on maintaining the integrity of causality underscores the intricate relationship between time, space, and the laws of physics. Engaging with these ideas can deepen our appreciation for the mysteries of the cosmos. Technological limitations present significant barriers to the feasibility of time travel and advanced space exploration. Current propulsion systems lack the capability to reach the velocities necessary for effective time manipulation. Until new technologies are developed, the dream of time travel remains largely theoretical. The energy requirements for achieving near-light speeds pose another major challenge. Our existing energy sources are inadequate for powering spacecraft at the levels needed for time travel. Research into alternative energy methods, such as nuclear fusion or antimatter, may provide solutions in the future. Moreover, the materials used in spacecraft construction must withstand the extreme conditions of space travel. As speeds increase, the stresses on materials also rise, which can lead to structural failure. Advances in materials science are essential for creating spacecraft capable of enduring high-velocity journeys. Radiation exposure is a critical concern for long-duration space missions. As astronauts travel beyond Earth's protective atmosphere, they become vulnerable to cosmic rays and solar radiation. Effective shielding technologies are necessary to protect crew members from harmful radiation effects during extended voyages. The limitations of our current understanding of physics also hinder progress in time travel technology. Many theoretical constructs, such as wormholes or time machines, remain unproven and speculative. Advancements in theoretical physics are needed to bridge the gap between our current knowledge and the complexities of time manipulation. Communication technologies must also evolve to accommodate the vast distances of space travel. As spacecraft journey farther from Earth, the time delay in signal transmission increases. Developing reliable communication systems that function over these distances is essential for effective mission coordination. Life support systems for extended missions present another set of challenges. Providing a stable environment for astronauts involves recycling air, water, and food over long periods. Ensuring these systems are efficient and sustainable will be crucial for the success of future explorations. The psychological effects of isolation and confinement during long missions are not fully understood. Astronauts may experience stress, anxiety, or interpersonal conflicts, which can impact their performance. Developing strategies to support mental health in space will be essential as we plan for future journeys. Furthermore, the technological infrastructure required for time travel remains largely non-existent. There are no established frameworks or guidelines for building time machines or stable wormholes. Creating this infrastructure would necessitate significant advancements in multiple scientific fields. The financial implications of developing time travel technology cannot be overlooked. Research and development require substantial funding, which is often limited by governmental and institutional priorities. Securing resources for such ambitious projects can be a daunting challenge. Advancements in artificial intelligence and robotics may play a crucial role in overcoming technological limitations. These technologies can enhance mission efficiency, improve data analysis, and support astronauts during long journeys. Integrating AI into space exploration could revolutionize how we approach future missions. The exploration of other celestial bodies, such as Mars or beyond, introduces additional technological hurdles. Developing the means to transport humans and equipment to these distant locations requires innovative solutions. Addressing the unique challenges posed by each environment will be key to successful exploration. As we push the boundaries of our understanding, the quest for time travel technology encourages interdisciplinary collaboration. Physicists, engineers, and biologists must work together to tackle the multifaceted challenges of space exploration. This collaborative effort can lead to breakthroughs that address technological limitations. The complexity of developing time travel technology highlights the intricacies of the universe. Each scientific advancement brings us closer to unraveling the mysteries of time and space. Embracing these challenges can inspire future generations to continue the pursuit of knowledge. The limitations we face today serve as stepping stones for future innovations. By acknowledging the hurdles in time travel and exploration, we can focus our efforts on finding viable solutions. The journey into the unknown demands creativity, determination, and a commitment to advancing human understanding. Time dilation experiments, particularly those involving atomic clocks, have provided significant insights into the effects of relativity. These experiments allow scientists to measure how time behaves under different conditions, validating the predictions made by Einstein's theory. By observing the discrepancies in time, researchers have gained a deeper understanding of the nature of time itself. One well-known experiment involved placing atomic clocks on high-speed jets. As the aircraft flew around the world, the clocks on board were compared to those that remained stationary on the ground. Upon their return, the traveling clocks showed slightly less elapsed time, demonstrating the effects of time dilation due to high velocities. Another significant experiment took place with clocks positioned at different altitudes. Atomic clocks at higher elevations experienced less gravitational pull than those at sea level. This difference in gravitational potential leads to measurable variations in time, providing evidence for gravitational time dilation as predicted by general relativity. These experiments have not only confirmed theoretical predictions, but have also practical implications. For example, the Global Positioning System, GPS, relies on precise timing to function accurately. Adjustments for time dilation effects, both from speed and gravity, are essential for the system to provide accurate location data. In space missions, understanding time dilation is crucial for mission planning and operations. The effects of time dilation must be considered when coordinating communications and scientific experiments. Ensuring that astronauts are aware of these factors can help in managing expectations regarding time and performance. Research into time dilation has led to advancements in atomic clock technology. These clocks are incredibly precise, capable of measuring time to within billionths of a second. This precision is essential for experiments designed to explore the subtleties of time and its relationship with space. The findings from time dilation experiments have also sparked interest in further studies. Scientists are continually exploring the effects of time dilation in various contexts, including the potential for new technologies. Understanding these principles can pave the way for innovative applications in both science and industry. As time dilation experiments continue, they contribute to a more comprehensive understanding of the universe. The insights gained from these studies inform our theories about time, space, and gravity. Each experiment provides a valuable piece of the puzzle in understanding how the universe operates. The implications of these experiments extend beyond theoretical physics. They challenge our everyday perceptions of time, prompting us to rethink how we measure and experience it. As we delve deeper into the mysteries of time, the results of these experiments encourage reflection on the nature of reality. Additionally, time dilation experiments highlight the interplay between technology and fundamental physics. The development of atomic clocks has not only enhanced our ability to study time, but has also had a transformative impact on various technologies. This synergy exemplifies the ongoing relationship between scientific discovery and practical application. In the realm of educational outreach, these experiments serve as engaging examples for students and the public. By illustrating the concepts of relativity through tangible experiments, they inspire curiosity and interest in physics. Communicating these findings effectively can foster a deeper appreciation for the intricacies of the universe. The continued exploration of time dilation also raises questions about future research directions. As technology advances, new methods for measuring time may emerge, leading to even more refined experiments. Each advancement has the potential to unlock further understanding of the complex relationship between time and space. In conclusion, time dilation experiments involving atomic clocks have revolutionized our understanding of time. They provide compelling evidence for the principles of relativity while demonstrating the profound implications for technology and everyday life. The ongoing pursuit of knowledge in this area promises to yield further discoveries about the nature of time itself. Muon decay provides a fascinating example of time dilation in action. Muons are subatomic particles created when cosmic rays interact with the Earth's atmosphere. They are unstable and decay into other particles in a very short time frame, typically around 2.2 microseconds in their rest frame. When muons are produced at high speeds, their decay times appear to stretch due to time dilation. According to relativity, as these particles travel closer to the speed of light, time for them slows down relative to stationary observers. This effect allows muons to travel farther than they would if they were at rest. Experiments conducted in particle accelerators have confirmed the time dilation effects observed with muons. When accelerated to high velocities, muons can travel significantly greater distances before decaying. This observable phenomenon aligns perfectly with the predictions of Einstein's theory of special relativity. One well-known experiment involved measuring muons generated by cosmic rays. Detectors placed at various altitudes captured these high-energy muons as they raced toward the Earth's surface. The data showed that muons reaching the ground were more numerous than expected, supporting the notion of time dilation. The results of these experiments have profound implications for our understanding of time and particle physics. They illustrate how time can behave differently depending on the speed of an object. This variability in the perception of time challenges our intuitive understanding of how the universe operates. Muon decay experiments also contribute to the field of high-energy physics. By studying the behavior of muons, scientists gain insights into fundamental interactions and the nature of particles. These investigations help to refine our models of particle behavior and inform future research. Additionally, muons serve as excellent probes for studying the effects of time dilation in real-world scenarios. Their relatively long decay time compared to other particles allows for easier observation and measurement. This makes them valuable tools for exploring the principles of relativity in experimental settings. The implications of time dilation extend beyond muons to other high-speed particles as well. Any particle moving at relativistic speeds experiences similar effects, demonstrating the universality of relativity. Understanding these behaviors enhances our grasp of the fundamental laws governing the universe. As technology continues to advance, researchers can conduct even more precise experiments involving muon decay. Enhanced detectors and accelerators allow for detailed measurements of time dilation effects. Each new finding contributes to a deeper understanding of the interplay between speed, time, and particle behavior. The study of muon decay and time dilation also informs discussions about potential applications in various fields. Insights gained from these experiments could influence developments in technology, such as improving particle accelerators or medical imaging techniques. The connections between fundamental physics and practical applications are crucial for advancing our understanding. The observations made through muon decay experiments reinforce the importance of empirical evidence in validating theoretical physics. The ability to measure time dilation directly through these particles provides a clear demonstration of Einstein's theories. Such confirmations deepen our appreciation for the intricacies of time and space. In popular culture, the concept of time dilation often captures the imagination, with references to fast-moving particles in science fiction narratives. These representations highlight the allure of exploring the unknown aspects of time travel. The scientific foundation provided by muon decay experiments adds credibility to these imaginative ideas. As research continues in the field of particle physics, muons remain a focus of investigation. Their unique properties and behaviors make them ideal subjects for exploring the effects of relativity. The ongoing study of muon decay and time dilation promises to yield new discoveries about the fundamental nature of the universe. Ultimately, the relationship between muon decay and time dilation exemplifies the intricate dance between theory and experimentation. Each experiment conducted enhances our understanding of time and the behavior of particles in motion. Engaging with these concepts allows us to explore the vast mysteries of the cosmos. Black holes are among the most mysterious and intriguing phenomena in the universe, profoundly affecting time and space. Their immense gravitational pull creates a warping of space-time that alters the way time is experienced. As objects approach a black hole, the effects of time dilation become increasingly pronounced. Near a black hole's event horizon, time behaves differently compared to regions further away. For an observer falling into a black hole, time appears to pass normally, but to an external observer, the falling individual seems to slow down dramatically as they approach the event horizon. This disparity highlights the relativity of time and the influence of gravitational forces. The concept of time dilation near black holes was famously illustrated in the film Interstellar. The movie depicted a scenario where astronauts visiting a planet close to a black hole experienced significant time differences compared to their colleagues in orbit. This dramatization emphasizes the profound impact black holes have on time perception. The intense gravitational field of a black hole stretches space-time, creating a sort of funnel effect. This means that any light escaping from near the event horizon is also affected, leading to a phenomenon known as gravitational redshift. As light struggles to escape the gravitational pull, it loses energy and shifts to longer wavelengths, altering our observations of distant objects. Inside the event horizon, the known laws of physics break down, leading to speculative theories about time and space. Once crossed, nothing can escape the gravitational grip of a black hole, including light. This makes it impossible for any information about what happens inside to reach an outside observer, raising questions about the ultimate fate of matter. The study of black holes offers insights into the nature of time itself. These cosmic giants challenge our understanding of fundamental concepts in physics and how they interact with gravity. By exploring the time effects of black holes, scientists can refine their models of space-time. Researchers are particularly interested in the relationship between black holes and time travel. Some theories propose that wormholes could form near black holes, potentially connecting distant points in space-time. However, the stability of such structures remains a topic of active investigation. Gravitational waves, ripples in space-time caused by massive objects like merging black holes, also reveal time-related effects. These waves carry information about the dynamics of their sources, allowing scientists to study events occurring in distant corners of the universe. Detecting and analyzing these waves further deepens our understanding of time and gravity. The possibility of time loops, where paths through space-time allow for circular journeys, is another intriguing aspect linked to black holes. Some theoretical models suggest that black holes could provide gateways to alternate realities or times. However, these concepts are still highly speculative and require further exploration. Moreover, black holes serve as natural laboratories for testing theories of relativity and quantum mechanics. Observing the behavior of matter and energy in their vicinity can yield valuable insights into the interplay between these fundamental theories. This research is crucial for advancing our understanding of the universe. Black holes also raise philosophical questions about the nature of time. If time can be altered or stretched by gravity, what does that mean for our perception of reality? Engaging with these ideas invites a broader examination of how we define and experience time. In addition, studying the effects of black holes on time has implications for future explorations of the cosmos. Understanding how time behaves near these enigmatic objects could inform our approaches to advanced space travel and exploration. This knowledge may pave the way for potential breakthroughs in the field. The allure of black holes extends beyond science. They have become a cultural phenomenon in literature and film. Their mysterious nature sparks the imagination and invites discussions about the unknown. These portrayals highlight our fascination with the cosmos and the possibilities of time. As we delve deeper into the study of black holes, we continue to uncover their secrets and complexities. Each discovery adds to the intricate tapestry of knowledge about time, space, and gravity. The journey into the heart of black holes remains an exciting frontier in the quest to understand the universe. Theoretical wormhole research delves into the fascinating possibilities of shortcuts through space-time. These hypothetical structures could connect distant points in the universe, potentially allowing for faster-than-light travel. Scientists and physicists explore various models to understand how wormholes might function and their implications for time travel. One popular model is the Einstein-Rosen bridge, which describes a type of wormhole connecting two separate regions of space-time. This concept suggests that if such a bridge could be stabilized, It might allow for instantaneous travel between the 2 points. However, the practicalities of creating and maintaining such a structure remain speculative. Research into traversable wormholes often involves the concept of exotic matter. This hypothetical substance would have negative energy density, necessary for keeping a wormhole open against the immense gravitational forces trying to collapse it. Currently, the existence of exotic matter has not been proven, posing a significant hurdle in the quest for practical wormhole travel. Additionally, the stability of wormholes is a key focus of theoretical research. Many models indicate that wormholes could be inherently unstable, collapsing before anything could pass through them. Understanding the conditions required for stability is essential for any future applications of these structures. Some physicists propose that manipulating the fabric of spacetime could allow for the creation of stable wormholes. This manipulation might involve advanced technologies or energy sources that we have yet to discover. Research in this area pushes the boundaries of our current understanding of physics. The interplay between quantum mechanics and wormhole theory has also garnered attention. Some researchers speculate that quantum fluctuations might allow for the temporary formation of microscopic wormholes. Investigating this possibility could lead to groundbreaking insights into the relationship between quantum physics and general relativity. In exploring the potential applications of wormholes, scientists consider their implications for time travel. If traversable wormholes could be created, they might allow for journeys into the past or future. This raises complex questions about causality and the ethical implications of altering historical events. Theoretical studies often use computer simulations to model the behavior of wormholes under various conditions. These simulations help researchers visualize how wormholes might interact with matter and energy. Such tools are invaluable for testing hypotheses and refining models in the absence of experimental data. Wormhole research has profound implications for our understanding of the universe. If they exist, they could provide insights into the structure and dynamics of space-time itself. This research may unlock new pathways for exploration and expand our comprehension of fundamental physics. Philosophical discussions often accompany theoretical wormhole research. The implications of traveling through wormholes challenge our understanding of identity, free will, and time. Engaging with these questions allows us to contemplate the deeper meaning of existence in a universe filled with possibilities. In popular culture, wormholes have captured the imagination of audiences through various media. From science fiction novels to blockbuster films, these concepts allow for thrilling narratives about time travel and exploration. This fascination reflects humanity's enduring curiosity about the unknown and our place in the cosmos. The study of wormholes can also intersect with other areas of research, such as black hole physics. Understanding the similarities and differences between these structures can deepen our knowledge of gravity and the nature of space-time. This interconnectedness highlights the richness of the field and the many avenues for exploration. As theoretical research progresses, scientists remain hopeful about the potential for discovering new principles related to wormholes. Each new finding brings us closer to understanding the complex interplay of forces that govern our universe. The exploration of wormholes serves as a reminder of the vast mysteries still waiting to be uncovered. In conclusion, the theoretical study of wormholes represents a captivating frontier in physics. The pursuit of knowledge in this area encourages innovative thinking and challenges existing paradigms. As research continues, we may uncover new insights that redefine our understanding of time, space, and the universe itself. Breakthroughs in quantum computing are revolutionizing our approach to information processing. Unlike classical computers, which use bits as the smallest unit of data, quantum computers utilize qubits. These qubits can exist in multiple states simultaneously, allowing for vastly more complex calculations. One significant advancement in quantum computing has been the development of error correction techniques. Quantum systems are notoriously fragile, and error rates have historically hindered progress. Researchers are now finding ways to protect qubits from decoherence, enhancing the reliability of quantum computations. Another noteworthy breakthrough is the creation of quantum algorithms that outperform their classical counterparts. For instance, Shor's algorithm allows for the factorization of large numbers exponentially faster than classical algorithms. This capability has profound implications for cryptography and data security. In addition, quantum supremacy has been achieved in several experiments, demonstrating that quantum computers can solve problems that are practically impossible for classical computers. Google claimed to have reached this milestone with their Sycamore processor, showcasing a specific computation in a matter of seconds. This achievement marks a pivotal moment in the field of quantum computing. The development of quantum hardware is also advancing rapidly. Innovations in superconducting materials and photonic systems are leading to more efficient and scalable quantum processors. As these technologies mature, they may bring us closer to practical quantum computing applications. Collaboration between academia and industry is driving many of these breakthroughs. Tech giants and research institutions are investing heavily in quantum research, fostering an environment ripe for innovation. This synergy is crucial for translating theoretical advancements into real-world applications. Quantum communication is another exciting area of development. Researchers are exploring how quantum entanglement can enable secure communication channels. This technology has the potential to revolutionize cybersecurity by providing unbreakable encryption methods. Furthermore, quantum computing holds promise for solving complex optimization problems. Industries such as logistics, finance, and pharmaceuticals could benefit from the enhanced computational power. These applications may lead to significant improvements in efficiency and cost-effectiveness. The integration of quantum computing into machine learning is also gaining traction. Quantum algorithms can process vast data sets more effectively than classical approaches, offering new insights and capabilities. This intersection of fields has the potential to transform how we approach data analysis and artificial intelligence. Ongoing research into quantum materials is uncovering new properties that could enhance quantum computing. Topological insulators and other exotic materials are being studied for their unique behaviors at the quantum level. These discoveries could lead to more robust and scalable quantum systems. In the educational sphere, increasing interest in quantum computing is prompting the development of specialized programs. Universities are creating curricula designed to equip the next generation of scientists and engineers with the skills needed in this rapidly evolving field. Training and education are vital for sustaining momentum in quantum research. Additionally, the concept of quantum networks is emerging as a frontier for future exploration. These networks could facilitate quantum communication and distributed quantum computing, allowing multiple quantum processors to work together. Building these networks will require addressing various technical and logistical challenges. The field of quantum computing is still in its infancy, yet the pace of progress is remarkable. Each breakthrough builds upon the last, creating a compounding effect in our understanding and capabilities. As we navigate this complex landscape, the potential for transformative applications remains enormous. Global collaboration is essential for accelerating advancements in quantum computing. Researchers around the world are sharing ideas, resources, and findings to push the boundaries of what is possible. This cooperative spirit fosters innovation and helps drive the field forward. Finally, the ethical implications of quantum computing must also be considered. As this technology matures, it raises questions about privacy, security, and the potential for misuse. Engaging in discussions about these ethical dimensions is crucial as we shape the future of quantum technology. In this exploration of time travel and its implications, we've covered a wide array of fascinating concepts. From the nature of time itself to the complexities of time dilation, we delved into the principles that govern our understanding of the universe. We also examined the potential of wormholes and the theoretical research surrounding them, highlighting the exciting possibilities they present. We discussed the ethical dilemmas associated with altering the past, considering the responsibilities of time travelers and the potential violations of causality. The implications of these concepts prompt profound questions about free will and determinism, inviting us to reflect on the nature of our choices. Furthermore, the role of technological advancements in making time travel feasible was a critical focus. The scientific breakthroughs in quantum computing, alongside the exploration of black holes, showcased how modern physics continues to challenge and expand our understanding of time and space. Each of these areas is interconnected, revealing the intricate web of knowledge that drives our pursuit of deeper insights into the universe. We've also highlighted the ongoing research into time dilation, particularly through experiments with atomic clocks and the study of muon decay. These experiments provide tangible evidence for the theories we've discussed, illustrating how empirical data supports our understanding of complex phenomena. As we conclude this journey through the multifaceted landscape of time travel and its implications, we encourage you to reflect on the possibilities that lie ahead. The questions raised in this video are just the beginning of a much larger conversation about our understanding of time, technology, and existence. If you enjoyed this video, please give it a thumbs up and subscribe to our channel for more content like this. Your support helps us continue to explore these intriguing topics and bring you more engaging discussions. Don't forget to check out our other videos, where we dive into a variety of scientific and philosophical subjects. Each video offers a unique perspective that can enhance your understanding of the world around us. Thank you for joining us on this exploration of time travel, quantum physics, and the wonders of the universe. We hope to see you in our future videos as we continue to uncover the mysteries that lie beyond our current understanding. Stay curious, keep questioning, and embrace the journey of learning with us. Together, we can explore the fascinating intersection of science, philosophy, and the boundless possibilities of time.